Welcome to everybody to this session of this satellite of opinion and language dynamics. I am going to introduce myself for those who don't know me. My name is Laura Hernandez. I am working in France. I'm a physicist. I work at Cergy Paris University in the west of Paris. And I am the leader PI of an international and interdisciplinary team that works on these subjects, with whom I am organizing the satellite. That is the third edition. I want to first thank all the members of a team that have helped the organization, and in particular to my postdoctoral researcher, Hendrik Schave, who dealt with all the technical organization. Here he is, and was extremely helpful. I will also want to thank to the organizers of this wonderful conference. I think it's an absolute great idea to mix these two communities that are working in nearby subjects, but are not always completely connected. I myself discovered a lot of interesting things. That was a real great idea, and I hope it's not going to be the last one. Thanks for this organization. Also, I want to thank to our two keynote speakers for having accepted our invitation. They have at least one thing in common, is that they... some problem. Okay, can we mute Mariano? Great. Okay, I was saying that our keynote speakers have one thing at least in common. They were both keynotes in IC2S2 last year. And there is where I heard their talks. And when I heard the talks, I say, okay, next time I'm going to organize something. These two are the ones that I would like to invite. And I'm very happy that they both agreed to be here. So that's going to be great. I will also want to thank to all the contributed speakers that I'm really keen to hearing the talks that I am sure it's going to be very interesting. So now a couple of instructions and then I stop. As you know, the keynotes have 45 minutes, which are 40 for the talk and 5 for the questions. The contributed is 20 minutes, 15 plus 5. I am going to disappear from the screen while you are talking, and then I'm going to appear 3 minutes before the end. When you see me turning on my camera again, means that you have to start to wrap up because you are about to reach your time. Okay. For the audience, it's possible to put the questions in the chat. It's a very good idea because we can see how you are getting in order, and we can take them, for instance, in order. But it is also possible, it has been configured as to let you talk. So you can turn your mic and your camera and do it as lively as we can in these circumstances. So just raise your hand and I give you the word. Okay, I think this is all. And without just talking more, I am gonna introduce our first keynote that is gonna open this session, who is Professor Filippo Menczer. Professor Menczer is a distinguished professor of informatics and computer science of Indiana University School of Informatics. And he is director of the Observatory on Social Media and former director of the Center of Complex Networks and Systems Research. He's a specialist of computational social sciences with a huge amount of contributions on the field. And so I give you the ground field. This is your time.
Thank you so much, Laura. Thank you for inviting me. It's really a pleasure. And I would like to share a little bit of the work that we do at the Observatory on Social Media here at Indiana University. As you mentioned, a lot of it is revolves around computational social science, and especially applied to understanding the spread of misinformation online and the manipulation of social media. So I have a sort of tongue-in-cheek title, which is 4 reasons why social networks make us vulnerable to misinformation. Let me share my screen here. There. Okay, so hopefully you can see it. So this is a clickbait title, which is in the theme of misinformation, but I actually will go over 4 different themes. The first one is echo chambers. Now, this is obviously something that we all hear about all the time, but our one of our contributions is to try to understand how the mechanisms of social media contribute to the vulnerability. So let me show you an animation of a model, a very, very simple model that we developed to illustrate how 2 ingredients that are common to all social media platforms contribute to this vulnerability. And the 2 ingredients are social influence and unfriending, selecting the people that we friend, and especially the ones that we don't want to friend. So this picture here, this network is a very simple representation of a social a community in a social network. The nodes represent users, the links represent social ties, and we assume that these users have an opinion, very simply represented here on a scale, you know, from progressive to conservative, which is represented by the color here. And this is a model that captures some of the very, very basic features that are present in all social media platforms. So people post things, the things that they post represent in some way their opinions, and then they also see things that are posted by their friends in a feed, and they may choose to retweet or reshare or repost some of the things that appear on their feed when they see them. There are few parameters, but the 2 main ingredients are the fact that when you are exposed to an opinion from somebody else, if it is close enough to yours, you may change your opinion a little bit to be more similar to what your friends posted. And also, when somebody posts something that you strongly disagree with, then you may decide to unfriend them. So let me start this simulation, and you can see that the dashed line here represent links that are cut, that are broken. So when somebody unfriends or unfollows somebody that they disagree with, and those links in this simple model are replaced with completely random new social ties, which are the solid lines here. So as the simulation runs, you see that a few things are happening. First of all, the distribution of the opinions is getting more narrow. Initially, you had sort of all the colors, and after a while, you see that the community is splitting into 2 groups, one which are mostly bluish and one that are mostly reddish. And there is less diversity within these groups. So the red nodes are all similar to each other, the blue nodes are all similar to each other. And at the same time, the users sort themselves into these groups where one is most likely to be connected to others that are similar to them. So we see these 2 phenomena, the polarization of the opinions into 2 homogeneous clusters. So you lose that initial heterogeneity, and at the same time the segregation of the network, so that the 2 groups become more and more separated until eventually at the end they become completely segregated. And this is an outcome that repeats over and over. You can run the simulation many times with various values of the parameters. Some things will change, for example, the speed with which this process happens. There are a few other parameters that may regulate depending on the tolerance of the users, how many groups emerge. It doesn't have to be 2, but in a broad set of parameters, you always end up with this outcome that, based only on these 2 ingredients, social influence and unfriending, inevitably you end up with these homogeneous and polarized echo chambers. So this is to illustrate how these basic mechanisms that are part of all of our platforms, whether it's Facebook, Twitter, Instagram, doesn't matter, very naturally accelerate our natural tendency to sort ourselves out into homogeneous community. An illustration of this, or of the consequence of this kind of polarization, comes from something that happened to our research group a few years ago. So, some hyper-partisan blog started posting some false claims about our own research, claiming that we were a secret government organization tracking or spying on citizens or trying to suppress conservative speech. This spread very fast through media like Fox News, and also fake news sources like InfoWars, and also Russian based propaganda sources like RT and Sputnik and so on. And of course, it also went very viral online with various hashtags that represented claims that kept coming up, all false, completely invented claims that our research about online manipulation and bots was really a secret political organization. Even claims that the FBI, that we were helping the FBI create a secret database to spy on citizens and things of that nature. So we were curious to see how this kind of disinformation campaign was spreading on Twitter. This is a network where, again, the nodes represent, in this case, Twitter accounts, and edges, the blue edges represent the spreading of these false claims. Links to articles that were, spreading falsehoods about our research. And there are a few edges here that are marked in yellow, which are actually spreading of fact-checking, which came out from reputable sources like Science magazine, for example. So then we try to look at how this network mapped onto the larger network of political communication. This was prior to the midterm elections in 2014. And of course, this political network is highly polarized, as we've shown before. And as you can see in this picture here, this is a retweet network. The conservatives mostly retweet other conservatives. The liberals mostly retweet other liberals. And the purple nodes in this larger network are the ones in the smaller network that I showed you before. So these are the people who are spreading the misinformation. We could think of them as a vulnerable population, the targets of this disinformation campaign. And you can see that most of them are on one side, in this case, the conservative side. And there is very few on the liberal side. And it's very hard to see here on the left, there is a couple of orange nodes. These are accounts that are actually sharing the fact-checking information. And so what you observe here is that one of the negative impacts of the polarization is that the people who are most vulnerable to a particular disinformation campaign, in this case, the conservative voters, are least likely to be exposed. They just don't see the corrections. The corrections may be there, but it doesn't matter because they don't see them, because nobody in their networks share them. And it could be the other way around. So, you might have disinformation campaign targeted at liberal people, and then conservative people might share fact-checking, but the vulnerable people would not see it. This was a few years ago, but things have not gotten better right now. This is a much more recent analysis. And we looked both at the follower network on Twitter and the diffusion network on Twitter. This is for people who are sharing links to news, not only news from reputable sources, but also news from low credibility sources. So these are sources that publish junk science, hyper-partisan, misleading content, conspiracy theories, and so on. And in both cases, whether you're looking at the diffusion network through retweets or the follower network, you see this very, very strong separation, polarization, and segregation. The size of the nodes here represents the fraction of one's links that are shared that come from low credibility sources. So the larger a node, the more an account is spreading information from low credibility sources. And you can see that there are large nodes on both sides, even though more on the conservative side, as has been reported in many papers by now by us and others. And so again, the echo chamber itself also make us more vulnerable to misinformation. And to explore this further, we developed a number of account bots. These are benign bots. We call them drifter bots. They don't have any intelligence. They do completely random actions. That's why we call them drifters. They kind of drift in the information ecosystem. There is only one thing that distinguishes between these different bot accounts, and it is the very first account that they follow. We initialize these bots by following a news source, and some of them follow conservative news sources, some of them follow liberal news sources, and the center, and so on. So we have them in 5 groups. And except for that one initial choice of the very, very first account that they follow, everything else is the same. They follow the exact same, very simple, dumb behavioral model. They basically follow people at random, that follow them, or retweet things at random, or that their friends post, and so on. But their initial bias of the very, very first friend leads them in different directions, okay? So the ones on the left tend to go on the left, or maybe sometimes towards the center. The one on the right tend to stay on the right, or even drift further to the right. And we see that all of them find themselves in these kind of echo chambers. These networks here represent their ego networks, so them and their friends and followers. And we can see that most of the times, the ones on the left tend to be surrounded by other liberal accounts. The ones on the right tend to be follow other conservative accounts. There are a few exceptions, like this blue cluster here, for example, started by following the Wall Street Journal, but then at one point followed CNN, which is a more liberal biased source in the opinion section. And so they started drifting towards the left. Here is another interesting example of an account that started following the Washington Post, but then also started following some more conservative accounts and ended up in a group that was not so homogeneous. But by and large, we see that these accounts end up in these echo chambers, and further on, the ones on the right are more likely to share links to low credibility sources. Like I said before, this is something that has been observed in our lab and others. So there's a strong association between conservative political tendency and vulnerability to misinformation. Now, we've also looked at this by looking at a larger collection of tweets, and tried to specifically study this correlation between political alignment and vulnerability to misinformation. Political alignment here is shown on the x-axis, and vulnerability or tendency to share low credibility links is on the y-axis. And actually, when you split conservative and liberals, you see that the correlation is on both sides. So it is actually stronger on the conservative side, but there is also a correlation on the liberal side. So this is to say that actually, it's not only conservatives that are vulnerable, liberals are vulnerable as well. In particular, the more you are partisan, the more you tend to focus on sources that are aligned with a more partisan worldview, the more you are likely to share links to low credibility sources. All right, so that's about echo chambers. Number 3 is information overload. This is also something that creates a vulnerability. Now, to illustrate this, let me start from this example. This is one particular piece of fake news that was spreading during the 2016 elections. It was the false claim that the Clinton campaign was involved in satanic rituals, and actually was a precursor to, we've all heard about, Pizzagate and QAnon, of course. So this is one of the early versions of that. And it was published by InfoWars, a well-known conspiracy theory source. And this network here represents the spreading of this particular claim. Nodes are Twitter accounts, edges are retweets. We see that some nodes are very influential. The size is proportional to the number of retweets. And these, of course, are the accounts associated with Alex Jones and InfoWars itself. And we also see that there is a bunch of other accounts that are also influential in exposing other people to this. And you can see that they tend to be colored in red. That means that these are likely automated accounts, and I'll come to this talking about social bots later. But here, what I want to focus your attention on is that this particular piece of false news was one of the most popular that was spreading in 2016. So this plot here shows the distribution of popularity, in this case, the number of tweets or retweets, but you can also measure the popularity by number of people and other ways, and the results are usually the same. And you can see that the distribution for both claims from low credibility sources and fact-checking sources, the distributions are quite similar. And it's very broad. As we know, there is a long tail. So most things are not very popular, but some things are extremely popular. And then low credibility sources have even a longer tail. So they have a likelihood of being very, very popular. So what are the reasons why some things are very popular? Why do you get this very long tail? So to explore these questions, we also considered an agent-based model, just like the one I showed you before. But here we're focused on the fact that on different set of parameters, different set of mechanisms. So the network in this particular case is static. We don't change the structure of the network, but we assume that users have finite attention. So they post things, and how much they post determines, sort of information load of the system. And then furthermore, they only retweet things from looking at some fraction of the things posted by their friends. Just like when you're scrolling on your Facebook or Twitter app or Instagram app, you don't necessarily see everything that is posted by everybody, but you see some of it. So we have a parameter that decides stochastically how many things you might scroll through before you decide what you might reshare. And so that's the parameter that captures individual attention. And it turns out that in a model like this, there are two ingredients that actually explain this broad distribution of popularity that we observe. And we must have both ingredients. One is the structure of the social network. If the network is a random graph, for example, we don't observe this long tail. We need a network that looks like social networks with hubs and high clustering coefficient. And the second ingredient is limited attention. If people have infinite attention, if they can look at everything that is posted by everybody before deciding what to reshare, then we don't see this long tail. But if people have a limited attention that they only see a fraction of what's out there, then you see this emergence of the long tail. Now, in this model, we are not assuming that the things that actually go viral are any better than anything else. Every meme in this model is just a random number. So the question is, well, people actually decide what they reshare. They don't reshare things at random. So what if people can tell the quality, which could represent anything that you want, interestingness, trustworthiness, and so on. Let's imagine that people can establish that quality here, and that the probability that you reshare something, a link, a meme, a hashtag, whatever, is proportional to the quality of that item. But this is, of course, limited among the items that you see based on your limited attention. So in this case, do the best ideas win? So the ideas that go viral, are they the ones that are the best? So we look at the correlation between quality and popularity. And we expect a positive correlation, of course. Here's what we find. We find that if the information load is low, that is, there is not so much information that is going around, and or the attention is high, that is, users can look at most, if not all, of the things that are posted by their friends before deciding what to share, then we are in information like the one on the left, where there is a high correlation between quality and virality and popularity. The size of the nodes in this network is proportional to the quality of the memes that the users share. So these big fat nodes mean good, right? Most of the stuff that is shared is high quality. On the other hand, if the information load is high and or the attention of the users is limited, then we see a very low correlation between quality and popularity. As we can see here, a lot of the nodes are small, which means a lot of the stuff that actually goes viral is low quality. So even if people can tell and prefer to share high quality information, their limited attention makes them vulnerable. So this is why, information overload creates another source of vulnerability. All right, that was number 3, information overload. Now, number 2 is platform bias. We hear a lot about platforms and their algorithms. So we've explored a couple of types of algorithmic biases. The first one is political bias. And to do this, we use these drifter bots that I told you about before. We tracked over time what they share, the links that they share, and the hashtags that they share. And based on that, we were trying to figure out whether these drifters were aligned with the initial sources that they followed or not. We looked at both their home timeline, which is what is shared by their friends, what they see, the information that they're exposed to, and the user timeline, which is what they post, the information that they actually produce themselves. And so we see in both cases that the bots that started on the left kind of drift towards the center. So there is a little bit of conservative bias here. And on the other hand, the bots that start on the right mostly tend to stay on the right and also even tend to post things that are more and more aligned to the right. So this in general paints a picture that there seems to be some kind of political bias. But is it caused by the platform? Some people claim that platforms have a political bias, especially we hear a lot of claims from conservative politicians that say that platforms have a liberal bias. Well, if anything, this would seem to be a conservative bias, but is that, could we attribute that to the platform itself? And so to study that question, we looked at the difference between the political alignment of what people see in their home timeline and what their friends actually post. And now we see that there is very little bias here. These curves are mostly around 0, which means that the algorithm itself is just representing what is posted by one's friends. So this political bias, conservative bias, we would not attribute it to the algorithm itself, but rather to the information ecosystem, to the fact that the right-wing ecosystem is very different from the left-wing ecosystem. There is actually more activity, there is more transitivity in the network, there is more retweeting, and so on and so forth. There is more following back, and the network itself is more clustered. So there are differences in the information ecosystem, and that affects the experience that an account may have online. So that's about political bias. We also looked at engagement bias. Now, of course, platforms let's assume that they like to share good quality things, but they also pay attention to engagement. Well, in part because they may have a financial interest in that, but also because engagement can be a signal of what people are interested in. This is the idea of wisdom of the crowd, right? If a lot of people share something, or if your friends share something, then probably it is interesting to you. So we built a model similar to the ones that I told you about, but now the items that appear on one's feed are ranked by an algorithm, which we have a parameter to measure how much the algorithm uses popularity as opposed to quality to rank items. And popularity can be inferred by how many people have previously shared an item. So think of it as a link to some news sources and so on. And so here on this x-axis, you see this popularity bias. We also have a parameter for attention, as I said before. And then on the vertical axis here, we have the average quality of information in the system. And we see that in general, the more there is engagement or popularity bias, the lower the average quality of of information in the entire system, in the entire network. So this suggests that popularity bias actually makes it more difficult for quality information to spread virally. Now, there is a narrow range of the attention parameter here in which a small amount of popularity bias actually helps, okay? This is the wisdom of the crowd. But it turns out that this wisdom of the crowd is something very narrow. In general, actually adding more popularity bias makes things worse. So what is happening here is not that the crowd helps find good quality information, but rather that some initial noise of things that initially go viral is then amplified by the algorithm. So popularity bias can hurt from a system perspective. But what about users? Okay. Well, users are also explored to information about popularity, right? Because platforms tell us, oh, this many people have watched this video, or this many people have retweeted or liked this tweet, and so on. Or there are these many comments on this Facebook post. So to explore this question, we actually we used an app developed in our lab called Fakey. You can use it if you want. It runs on on your phone, and it simulates actually builds a feed similar to Facebook or Twitter with links to low credibility and mainstream sources. And we use it for literacy. So students, for example, in schools can use it to learn to recognize sources. And the reason is that when you see a news, you don't know the source, but you have to decide whether to share it or like it or flag it for fact checking. And you get points for doing the right things, right? For flagging things that are from low credibility sources and sharing more reliable sources. And so what we observed here, though, we did an experiment where we manipulated this engagement signal here. And what we notice is that when people think that an item is more popular or has higher engagement, they're more likely to share, even if it's a low credibility article. And furthermore, if they think that something is highly popular or engaging, they're less likely to fact check. And again, this is for low credibility articles. So even the mere exposure to these engagement signals create a vulnerability. Because we are we're biased. We think other people like something, we think it is more worth sharing. Okay, so that was number two, platform bias. And then number one is manipulation. And this is actually where most of the research in our lab is focused. We worked on social bots for many years, starting over 10 years ago when we discovered the first instances of social bots. We actually coined the term social bot. These two accounts here were two social bots that were promoting a particular politician here and retweeting each other thousands and thousands of times, which was represented by this very large blue edge. We were drawing the network and we were making the weight of an edge proportional to the number of retweets. And we thought there was a bug in our code. And then when we saw this huge blob of blue, and then we realized, no, it was actually correct. This edge is so thick because these accounts are retweeting each other thousands of times. And then when we looked at it, it turned out that they were automatic accounts. So we've been studying bots for many years. Here on the left, we have another example of a bunch of accounts that were not necessarily automated, but they were all controlled by one person who posted fake news articles in a fake news source, and then used these accounts that he controlled to tweet links to these false news articles and mention a person that is the node in the middle, an influential journalist or politician, hoping that they would retweet and so that the false news would go viral. So these represent some of the strategies that we observe in bots. One is flooding. Another one is targeting influential accounts. And also this idea of coordinated campaigns, which is something that we're studying more now, and I'll tell you about it more in a second. So during 2016, we built this system called Hoaxy, and we collected lots of links to low credibility and fact-checking sources, and we looked at how links to these sources were sharing on Facebook. And we find another kind of echo chamber here. In purple, these are the sharing of low credibility sources, and we see that people who share low credibility sources mostly connect and retweet other people who are also vulnerable to misinformation and are less likely to share fact-checking information. And furthermore, as we dive into the core of this misinformation network, we see a stronger and stronger presence of accounts that are likely automated. This is the bot score, which is computed with our tool Botometer. I'll tell you more in a second. But basically, it's something that gives us the likelihood that an account is automated. So the more you go into this vulnerable community of people sharing misinformation, the more you see that bots are very active there. With our drifters, we also observed this. We saw that there is a correlation between bot presence and political alignment, in particular among friends. So if you look at who these bots follow, you see that the more the bots are partisan, the more they're likely to follow bots. So this is another source of vulnerability where the political alignment and the structure of the network and the presence of manipulation are all connected to each other. Because bots, of course, can easily target vulnerable populations. And we saw before that accounts that are highly partisan are more vulnerable. So what do bots do? We studied some of their strategies and behaviors. One thing I already mentioned is that they target influential users. So the more an account is likely to be automated, the more it's likely to mention other accounts that are highly influential in terms of number of followers. I'll give you an example here. This yellow dot here, this was actually a bot that was very effective during 2016. It did something very clever. It replied automatically to any messages from mainstream sources like CNN and Fox News, New York Times, BBC, whatever, if they mentioned Donald Trump. Okay, so if these news articles mention Donald Trump, this bot would automatically reply to the message, and in the reply, it would have a link to a false news article. And it was this article at the top here, see, 3 million votes in presidential election cast by illegal aliens. This was a false claim from InfoWars that the reason why Trump had lost the popular vote against Clinton was because illegal aliens were voting. This was completely unfounded, but this bot was really trying hard to get Donald Trump to see this claim. And so the red links in this network represent mentions. And so that's why there is a very, very thick link between the Donald Trump account and this bot account. And so Donald Trump would then get the impression that these news sources were talking about him and were discussing this article. And this was done in an apparent attempt to get Donald Trump to read that article. And we know that sometime later, Donald Trump actually repeated this claim and said that he had seen an article with this claim. And we did a lot of searching, and the only source of this claim was this article in InfoWars, which attributed this claim to an account that had already been suspended by Twitter, an anonymous source. So, so this is a way in which inauthentic accounts can be used to manipulate this information and amplify this information. Another interesting observation is that when you look at this information that spreads virally, what we did is we kind of went back in time. Now, by the time something is viral, if you look at who's retweeting something, it turns out to be all sorts of regular people. But if you can go back in time and see what are the first accounts that retweeted these links to low credibility false news, low credibility sources, if you look at the first few seconds, like 10 seconds, then you see that those accounts have a very high bot score. So this means that bots are used in the early phases to amplify a message and get other people to be exposed, humans to be exposed to this disinformation. But later on, you don't see that presence anymore because these bots are washed out among thousands or tens of thousands of regular users. But clearly, these are accounts that are coordinated with the sources. So the source posts something and then has this army of inauthentic accounts that reshare it to get that amplification to trick both users and algorithms, platform algorithms. And then the third strategy, of course, is flooding. So you see that the same account can share the same link to the same false claim thousands of times in some cases. So this is the classic flooding strategy, and we're still studying how bots can get around some of the limitations of platforms and tweet at very, very high volume, even higher than the platforms allow. So in terms of impact, we can look at, for example, retweets. We can see who is retweeting links to low credibility information, who's doing the tweeting and who's doing the retweeting. So this is for retweets. And on the x-axis, you have the bot score of the retweeter, and on the y-axis, the bot score of the original tweeter. And if we project onto the x-axis, we can see that most of the retweeters are humans, are likely humans. But if you focus on those humans and you look at whom they are retweeting, who are the sources that are being retweeted with these low credibility links, you see here the projection on the y-axis. You see that humans retweet other humans, but they also retweet bots. So this is one way in which we can clearly see the impact of bots. They get humans to be exposed to something, as we saw in the earlier network. Remember those red dots? Humans are exposed to this misinformation by bots, and then they reshare it themselves. We've been talking about bots, but like I mentioned earlier, there is a lot of manipulation that can be done without any automation. So here's an example of an account that if you look at it, it's not automated at all. This is clearly run by a human. It looks like an anti-Trump political account, maybe nothing particularly suspicious with it. But now what if I show you all these other accounts? And now you'll say, oh, okay, that looks fishy, right? Because these accounts are using the same images, and they are using very similar patterns and templates to create these accounts with uses of hashtags and links to websites, except that some of these are anti-Trump and some of these are pro-Trump. So these are accounts that are controlled by one person, one entity, to do fraud, actually, to get donations. They claim to be part of campaigns to get political donations, but in fact, they're just, committing fraud. And they target, of course, vulnerable partisan people. And so we've done a lot of work to try to detect these kind of inauthentic networks. And we find lots and lots of examples. So this network, for example, is based on accounts that share the same handles, because some accounts rotate and share the same handles to avoid detection of suspicious activity by Twitter. So we find networks with hundreds of accounts that share and the same set of handles, and they just alternate among them. That's how we found, for example, this network that I showed you earlier. And some of these networks are pretty large. We also find suspicious networks in many other domains. So, for example, we looked at accounts that suspiciously retweet the same tweets in the context of spreading misinformation about COVID, and we find these dense clusters of suspicious users. We looked at Hong Kong protests. We found coordinated groups that share the same exact images, suspiciously large sets of the same or very, very similar images, and we found them on both sides, pro and anti-protest groups. We found accounts that retweet the same accounts in disinformation campaigns targeting white helmets in the Syrian civil war. When we looked at cryptocurrencies, we find a lot of pump and dump fraud. And here we find clusters of accounts that are clearly bots and that are coordinated because we noticed that they post at the exact same times. Okay, so here similarity is measured based on temporal synchronization. And so these are networks that try to pump up the price of some cryptocurrency before dumping it and trying to make money. It's a type of financial fraud. And then we see, of course, this kind of manipulation in politics. We find large clusters of accounts that share exact identical sequences of hashtags, for example. We find this both on the left and on the right. And this happens in a number of ways. For example, people who donate their Twitter credentials to an app, they let an app tweet on their behalf, for example, a political campaign app. Or we find communities that are paid by political groups in order to post links. So this was an article in the Washington Post where we did an analysis and found these teens in Arizona that were all tweeting slight variations of basically doing the copy pasta approach of messages that they were given by political operatives on a Google spreadsheet, and these teams were paid by based on the number of tweets that they generated. So they created a lot of fake accounts, and we could identify them because they were lazy and they were posting exactly the same messages. And so this is widespread kind of abuse. So whether accounts are automated or not, if they are coordinated, they could have a large impact. So we use the model similar to the one that I was telling you about before to look at how well a coordinated campaign run by a number of coordinated accounts can affect the quality of information in an online community. Now, if these accounts have a low infiltration, they stay kind of on the periphery of the group, they don't have much effect. So the human accounts here in gray, their color is the number of low credibility information that they share. And you see that there is some dark color, but there is also a lot of light color. But if you increase the infiltration, if you allow these accounts to be followed by many users, as this actually happens in the real world, if these coordinated campaigns can successfully infiltrate a community, then they can drive the overall quality of the information shared by this community way down. So as you can see here now, the humans are sharing mostly low credibility information. Most of them are very dark. So this is an illustration of the damage that can be done by these coordinated accounts. I know that I'm almost running out of time. I see Laura there. As I wrap up, let me just mention that on the Observatory on Social Media website, we have a number of tools. And you're welcome to play with them. We have Botometer, I mentioned it before. This is a machine learning tool that you can use to look at an account and tell whether it's potentially automated. We also have Hoaxy, a visualization tool where you can track the spread of information, memes, links, and so on. You can look at, it's connected with Botometer, so you can look at whether accounts that are highly active in spreading some narratives are automated or not. And we have a new tool called BotSlayer, where you can set up your own infrastructure in the cloud, tracking, for example, some hashtags of interest or keywords or whatever you want. And you can see whether entities associated with these narratives are spread suspiciously by accounts that are likely coordinated or likely automated. So, for example, using this, we found in real time a campaign that was targeting Bill Browder with links to a fake news video that was amplified by a number of Russian bot accounts that were taken down by Twitter literally seconds later. And the latest tool that we have is called Covaxi, and it looks at the connection between vulnerability to vaccine misinformation, in fact, hesitancy and low adoption of vaccines with the spread of misinformation about the vaccines at the state and county level. So I will finish here to summarize. What we're looking at is the interplay of cognitive, social, and algorithmic biases and how they make us vulnerable to misinformation. And of course, how bad actors, whether they're automated or not, can exploit these vulnerabilities. So tools to study these information diffusion networks, bots, and coordinated campaigns hopefully can help us understand and counter this kind of manipulation. I want to thank all the students and my colleagues in our group. This is really the work of many, many people, not just mine. And also my gratitude to our funders who support this work. Okay, thank you so much. I hope there is some time for questions.
Thank you very much. Phil is perfect in time, like perfect. Okay, great. So time for questions. So you can just raise your hand, and let's put everybody to see if there are any questions. There is already one demand in the chat. Is the Osnat Mokrin says, thank you, very, very interesting. Would you be able to share the links on the chat or share the slides, please? Okay, the links, I suppose, to the last platforms that you were talking to.
Okay, I just posted a link to our website, and a lot of this material is there, including videos, slides, papers, of course. So that's a good starting point. And if you want to publish the slides on the workshop website, I'm more than happy to share them as well.
Perfect. That's a great idea. Thank you very much. Okay. Any other question?
Yes, Laura, can I ask a question?
Yes, go ahead, Marionisa. Just put your camera and go ahead.
Yes, thank you very much for your great talk. Could you tell us what kinds of criteria of relevance did you use to define misinformation? And
Mhm.
why do you think that the conservative people are more vulnerable to misinformation in the echo chambers? Thank you.
Thank you for that question. So first of all, I should distinguish between two different kinds of studies. In the modeling studies, of course, we have the luxury of just defining what we want. So, we can have a simple measure of this information. We could say that some things is low credibility. We can generate this trustworthiness or credibility variable from some distribution. So that's kind of arbitrary and easier to do. For empirical studies, where where we're actually trying to measure these things in the wild, what we do is we use sources of media, of news sources that are compiled by third-party journalists and fact-checking organizations. This is the approach that is done by most research in this area. And there's various sources that list low credibility sources. There are also some organizations that provide data, which unfortunately, well, in some cases it is free, in some cases it is not free, but they provide indices or basically values that can be used to quantify the reliability of a source. So they look at, for example, how frequently a source posts something that is debunked by fact checkers, or whether they post corrections and things of this nature. So there are ways, the simplest one is Wikipedia. Wikipedia maintains a list of low credibility sources. And by the way, these lists change over time. So we have to always keep current. But we use these third-party sources, depending on the different kind of study, either to assess the quality of a source, or to simply have like two classes of reliable and unreliable sources. We do this at the source level, because doing it at the article level is simply impossible. We just don't have neither automatic ways to detect whether a piece of an article is reliable or trustworthy or not, nor do we have scalable approaches using human fact checkers to do this. And so most of the literature in this area labels items at the source level, which is not perfect, of course, because you might have a reliable source that occasionally posts something that is misleading, although usually they post a correction. And you might also have a low credibility sources that occasionally will post a reliable source. So for example, we have some fake news sources that occasionally copy and paste articles from mainstream sources, and then either the way that they are, just with a misleading article title, just by adding a title, or by making very small tweaks. And so sometimes you may have an article that is mostly accurate, but still slightly misleading in some way. So it's impossible to do it at the article level, and we do it at the source level. Sorry, the second question you asked is why conservatives are more vulnerable. This is a much harder question, of course. I would say the result is robust because there are many publications now who have found the same effect. There are different theories. Some argue that conservatives are more vulnerable because of their own cognitive biases. There's some theories in moral psychology that look at different kind of values that are espoused by conservative and liberal people that naturally make conservatives more vulnerable, because they are more skeptical of certain authorities or science or government and so on. Maybe this is part of the explanation. I don't know. This is not my expertise. There are other theories that say that this could simply be a historical accident. At the time in which people started to realize that they could manipulate social media at the time where fake news sources became very popular online on social media and became weaponized. Of course, misinformation has always existed, but social media have not. And so the fact that people now access news through social media means that many more people are vulnerable to this kind of manipulation. And at the time where this was happening, this was a time in which conservatives' narratives, including some misleading ones and some false ones, became very, very popular. And so, in particular, between 2010 and 2016, and exploding in 2016 and after, we've seen a lot of manipulation that has exploited this kind of vulnerability, especially on the right. Now, this may have happened on both sides. So, for example, you may remember that the Russian IRA accounts were targeting both conservatives and liberals. They were creating fake persona, impersonating Black Lives Matter movements, for example. And so they were actually able to fool people on both sides. However, the response on the right was stronger. And also fake news websites soon realized that messages that echoed conservative narratives were more popular and more successful. So this is not an answer to your question. I think this is something that is still open for research. There could be a combination of different factors, and we'll have to study more. I actually think that people on the left are vulnerable too, as we have shown, but it's not symmetric.
Thank you.
Okay, there is another question from Alexandre Beauvais. Do you want to turn on your camera, mic, and put it yourself?
Hi, can you see me?
Go ahead. Yes, go ahead.
Yeah, I just wanted to thank you for the really interesting talk. And my question was, what do you think that platforms like Twitter can do to help with these issues? And also, are they listening to you, or are they willing to work with you?
That's a very good question. I think the situation is fluid. I think for the first few years, the platforms were very reluctant to accept and admit the fact that they were being manipulated so effectively. But in the last few years, based in great part to very strong popular reaction and PR type of things, they are now seem to be more responsive, and their policies have been changing enormously. They have become much more aggressive in implementing their own algorithms. Unfortunately, they're secret, and we cannot audit them, and we cannot see how well they're working. And maybe that's something where things can get better. But they've certainly become more aggressive. Twitter, for example, has become much more aggressive in detecting automated accounts. Of course, as with any difficult adversarial machine learning problem, if you're more aggressive, you'll get more of the bad actors, but you'll also catch a lot of the good actors. And so we see a lot of legitimate accounts who are being suspended, and then they have to work very hard to get Twitter to listen to them and unsuspend their accounts. However, we've seen that during the last election in 2020, they were quite effective. For example, they did something that we and others have suggested in adding some friction. I've argued, and others have argued as well, that one of the vulnerabilities come from the ease with which accounts can flood the network by posting at very high volume. And so because it's so easy and free to post and share information. So Twitter, for example, have slowed down that process. They've decreased the number of tweets that people can post, although I think it's still very high. And they've also added some captchas or some checks, forcing people to prove that they are humans if they post at high rate. And so I think that these measures can be effective. Some of them are still in place, some of them have been taken down. Facebook, of course, is also aggressive in taking down fake accounts, but I think they are so flooded that a lot of stuff goes through. I, as a regular user, sometimes flag inauthentic accounts, and then I get a response from that says, oh, no, we don't see anything wrong with this account, where it is so obvious and clear that this is a fake account. So I think there's a lot more work, and platforms have to work harder to work with researchers, but I think there is some movement in the right direction. So for example, both Facebook and Twitter recently have launched programs to make it easier for researchers like us to access their data. So Twitter, for example, has a new academic API. Facebook has announced, has reopened the Page API to authorized researchers. So to answer your question, there is some movement in the right direction, but there is probably still a lot more work to do, especially in terms of transparency. I'll mention one example. We, our research, is focused a lot on recognizing social bots. And although we're not directly working with Twitter on this, Twitter is very aware of our research, of course. We know that from talking to them. And so we imagine that perhaps some of the ideas that come from our research perhaps are incorporated in their own system. However, when they suspend an account, we cannot see anymore what that account did in the past. And so our own research on what manipulation is effective or not effective, or how their own countermeasures are effective or ineffective, is hindered. Because as researchers, all of a sudden, we do not have access. In fact, we get data from Twitter, a sample of tweets, and we must delete all tweets by accounts that are removed by Twitter in order to get access to this data. And so that hinders our own capacity to study this kind of phenomena. So yes, things are getting somewhat better, but there's still a lot of work to do. Thank you for that question.
Okay, I'm sorry, I have the bad role. We have to move on, so I'm sorry, I'm going to frustrate some questions that are still on the chat. Maybe, Phil, you can answer to them in the chat.
Yes.
I do that by frustrating even myself, but we are just 6 minutes late. Thank you very much.
Thanks, everybody. I will answer any questions on the chat. I'll stick around.
Thank you very much. So now I am calling Jafar Mansouri.
Yes.
Can you, maybe you are not sharing, so go ahead. You can try to share your screen. Okay, yes. So the next talk is by Jafar Mansouri, is joint work with Fabrice Cavaretta, Wasim Souaile, I hope I pronounced correctly, and Dimitrios Kosinos. This is joint work from two laboratories, ETIS Lab at Cergy Paris University and ESSEC Business School also at Cergy. So you have 15 minutes talk starting now. I'm the counting.
Yes, hello. Thank you very much for your introduction. I am going to talk about our work completely unsupervised opinion mining in professional groups discussions. Nowadays, with explosion of the social online discussion on different social media platforms like LinkedIn, Twitter, or Facebook, we can have access to a large amount of the text, but this text has special characteristics. For example, these texts usually are very short. They contain emojis, links, target, and sometimes typos. The grammar rules are not correctly respected. And one of the most important things is that any user can write about every topic. So we have diversity of the topics. One interesting subject and topic is that how we can distinguish and separate a special discussion for a professional group from the public discussion. It can be, for this task, there are some problems that should be considered. First, we need to separate the target groups. The other problem is that even the group members from one group can tweet, for example, can post some text about every topics. So we have a diversity of the topics. And the other issue is that how we can identify this specific subject of interest without human intervention and without prior knowledge. The reason is that if for some application of social sciences, if we have the bias and we have the human intervention, we can have the bias, and this can affect the classification results. In other words, for example, one person can say that one post is related to, for example, business, and other person can say that that post is related to the politics. So we should avoid the supervised classification methods due to the innate bias of the nature of these algorithms. We can use the unsupervised methods, but they are also problematic since if we do not have any ground truth, the evaluation of the classification result is very tough and problematic. In this project, we propose a completely unsupervised method without human intervention and without any prior knowledge for identifying a specific discussion from a professional group's tweets. So the target groups are entrepreneurs, and they are identified by this way that we find the tweets that the user specified and describe themselves as entrepreneurs on their profile descriptions. Of course, it can be, there are some problems for this. Maybe there are bots, or for example, or maybe there are some temporary entrepreneurs, but we can assume that this number of the users are very few. And the most important thing is that how we can discriminate discussion of the entrepreneurs from the public discussions. By that, I mean that the discussion that are commonly shared between entrepreneurs, but the public user usually do not use this discussion in their tweets. And we want to propose a method that it can be generalized for any professional groups. We have 4 stages: data collection, pre-processing, unsupervised scoring algorithm, and unsupervised tweet classification by the convolutional neural network. For collecting the tweets, we use the TweetPy API, and we had 2 phases. On phase 1, we first collect random tweets by the API, and then we cluster the user to 2 groups, and the entrepreneurs and the public users. And in the second phase, by this TweetPy, we can collect maximally 3,200 tweets from each user. We can collect different information like username, user ID, language, time, and date of the tweets, location, and profile description. We have collected about 47 million tweets from about 24,000 entrepreneurs and about 53 million tweets from 38,000 public users around the world. And the date is from September to 2020 and back. The reason is that we collect the public tweets is that the public set plays the role of a control group, and it expresses the public discussions. We can create the set of the tweets by the different features. For example, if we want to create features just by the tweets and the corresponding user, we can have, for example, this kind of the image that we have the user and their corresponding tweets. The second stage is the pre-processing. As I mentioned, the tweets contains many, for example, targets, emojis, links, and others. So, the most important, it is very important that we do the tweet cleaning. We have 2 steps: removing common stop words, emojis, targets, links, numbers, and punctuations. And after that, we do lemmatization. For example, if we have one tweet at John AI is used in the business with a link, after tweet cleaning, we have AI use business. Then when we do the tweet cleaning, we go to the unsupervised scoring algorithm. And the aim of this algorithm is to discriminate public discussion from the specific discussion for the entrepreneurs. And the idea is that usually a specific group of the people use a specific words or combination for expressing their opinions and their discussions. So we can say that if they appear frequently in one set and they are not used many times and frequently in another set, they can be a good sign for the discrimination. By this, we can give more weights to these words or combination of the words. For this purpose, for every tweet, we can, for every set of the tweets for interviewers and the public, separately, we find all of the words and all of the combination of the words in each tweet and find their frequency. Here, frequency means that how many users have used one word or one combination of words in their tweets. And so in this case, every word or every combination of the words is just counted once for each user. After finding this frequency for all of the words and all of the combination of two words, we can find a weight for every word or every combination of the words by using this formula that it expresses the relative normalized frequency of words in the entrepreneurship dataset. Similarly, we can do this we can find this weight for the combination of the two words in the entrepreneurship dataset. But here we multiply the weights by 2 since we want to give more weights to the combination of the words. The reason is that using one combination of words is more informative than one word in a tweet. After that, we can, for every tweet, we can find a normalized score using the weights for every word and every combination of the words in the tweet using this formula. That has been shown. And so we have for every tweet, we have one score, and then we can sort the tweets based on the scores. And we can consider one hypothesis. The hypothesis is that when we have a score with more positive, when we have a tweet with more positive scores, it means that it is very likely that it expresses the specific discussion for the interviewers. On contrast, when we have a tweet with more negative scores, it means that it is very likely that it is tweeting about the public discussions. Now I give you one example for the scoring algorithm. For example, as I mentioned before, at John, AI is used in the business with a link. After killing, we have AI use business. So we have 3 words and 3 combinations of the words. And we can find the relative weights for each word and in combination of the words. And for that tweet, we can find the score for it. So for example, for this tweet, it has the score of 0.22. So it means that it is very likely that this tweet is have a discussion for the interviewers with this scores. And then the important part of another important part of our project is using the CNN. CNN is used for 2 purposes. And the first is to confirming the scoring algorithm that whether it works well or not. And the other task is to do tweet classifications. And for the experiment, in this case, we can select, we can have different cases for training the neural networks. We can select the most positive scores for the tweets or tweets with the most negative scores, or the tweets with the most, the less positive and the less negative score, or we can select randomly from the positive or negative scores. In every case, we have experimented it with 2 million tweets from entrepreneurship and public sets for the year of 2018. And in each case, we have a different kind of the number of the tweets. But in every case, we use 70% of the tweets for the training, 10% for the validation, and 20% for the test. For example, if we use the case 1, we have 500,000 tweets totally. So we give this tweet cleaning, but here the tweet cleaning is light. It is not very heavy like before. By that I mean that first we remove the links, targets, and emojis, but we do not remove any punctuation, any stop words. And then by every word or every token in the tweets is converted a vector by using the fastest algorithm. So the embedded negative tweets and embedded positive tweets are given to the CNN to be trained. After training, we give the test tweets to the CNN to give us the decision for these tweets. Here, because we do not have the ground truth, we assume that the scores found by the scoring algorithm can play the role of the ground truth. So in this case, we can find accuracy for the validation and for the test. As I mentioned here, we can see that when we use the tweets with the most positive score and the most negative score for the training, we can have a very good result. And it confirms that even the scoring algorithm works very well, since we have a very good result even for the validation and for the test. So it can give us two things. First, the scoring algorithm is working very well. And the second case, the second thing is that we can use it for the tweet classification for the rest of the tweets. For the future works, we aim to extract beliefs unsupervisedly from the specific discussion for the entrepreneurs. We should notice that it is different from the sentiment opinion mining that is usually considered in the literature, because we want to find the beliefs, and or in other words, the key concept that tweet is written about. The beliefs can be expressed in any one or more words in any part of the tweet. For example, in AI is used in business, the beliefs can be AR or business. Beliefs usually can be expressed in the factual sentences and sometimes in the sentimental ones. But for the sentiment analysis, as it has been done in many papers, usually they are in the sentimental sentences, and we have one aspect, the thing that we have the negative or positive view regarding to that. For example, in AI is important in business. It is a sentimental sentence that we want to say that using AI in business is important or is a good thing. So we have a positive view regarding to this. To conclude this presentation, we propose a fully unsupervised method for identifying a specific discussion for the entrepreneurs by two algorithms, a scoring algorithm and CNN. The scoring algorithm is based on this fact that every group, a specific group, use special words or combination of the words to express their opinions and the discussions. Also, we use the CNN. CNN is used for two tasks. First, confirming the hypothesis of the scoring algorithm, that it works well or not. And also for the tweet classification by the tweets, candidate tweets that we have found by the scoring algorithms. Thank you very much.
Okay, thank you very much, Jafar, for this talk. Is there any questions? Let me see the chat. Are there any questions? Sorry for this. No questions? Please, if you want, you can raise your hand and talk directly. Okay, I just have one question out of curiosity. It was very quick and I'm not sure that I saw it correctly. When you were discussing the neural network, can you put a slide? Because I had the impression that you get a better result when you train with much less tweets, but of the same kind. And I was finding this one.
Yes,
exactly.
the third case. Yes, we have different cases. We can select the tweets from the most positive and most negative scores. We have three cases, 250,000 tweets from each scores, or 150,000 or 50,000 tweets. In this case, actually, the accuracy are very close to each other, but differently, when we have fewer tweets, it can give us the high accuracy, but the problem is that the power of generalization decreases. Since we have fewer tweets, it gives us good accuracy, but the power of generalization can be decreased.
Okay, yeah, I understand. Okay, thank you very much. Any other question? Let me check the chat. Okay. Well, if there are no more questions, let me see that I'm not skipping anybody. On the right, no, it's okay. Okay, thank you very much for your talk.
You're welcome. You're welcome.
I am now calling Muhammad Salashur. Is Muhammad here? Hello. Okay, Muhammad is from Max Planck Institute for Mathematics and the Science at Leipzig in Germany, and he's going to talk about biasability and noise information propagation in social and biological networks. Okay, again, 15 minutes plus 5 questions.
Thank you very much. I am going to argue that biostability, being on an age of biostability and an optimal amount of noise can improve information propagation in social and biological networks and optimizes the use of information. My talk is based on my paper, Phase Diagram Optimal Information Using a Collective Sensing System, published in Physical Review Letters. I begin by giving a motivation behind this study. Individuals in many biological and social populations live in uncertain environments in which the environmental conditions is subject to change and fluctuations. Individuals in such population need to constantly monitor the environment and update their beliefs regarding the environmental conditions. In many cases, they do this collectively and by exchanging information between the individuals. In such cases, individuals need to address different challenges. They need to combine social information provided by the communication between the individuals or simply by observing others' choices with personal information provided by direct observation of the environment to make optimal or better decisions. In addition, in a fast-changing environment, in a changing environment in general, individuals need to make fast decisions, but also their decision needs to be accurate enough. How they manage to do so? To address this question, I will introduce a simple mathematical model, but before proceeding to the model, let's have a closer look at the phenomena of the interest. In many social and biological population, social information can be obtained by simply observing others' choices or imitating others. Examples in biological cases can be an individual in a collectively moving population where an individual can obtain social information by observing the motion of others, or humans in or generally in social systems where individuals can obtain social information by observing other choices or simply imitating others. But also in many other cases, individuals can obtain social information by communication between themselves by production and comprehension of signals, where an individual, the transmitter, produces a signal to communicate a piece of information, and another individual, the receiver, or a set of individuals, the receivers, comprehend the signals. Examples range from bacteria and cells in multicellular organisms who communicate by exchanging chemical signals, to insects in social and eusocial species who communicate by exchanging chemical, tactile, and visual signals, to animals, and even human language can be considered as a highly evolved version of such communication systems. Despite being widespread in biological and social systems, most of the models, mathematical models on the subject on collective information acquisition or opinion dynamics, have generally considered a simple imitation process. A characteristic of the model that I present here is that communication by exchanging signals is taken into account. But what is the model? In this model, I consider a population of individuals who live in an uncertain environment, which can be found in n possible states. Individuals have access to n representations, each corresponding to one of the environmental states. and they can produce and comprehend n possible signals, each corresponding to one of the representations. For this purpose, they are equipped with 3 information channels: an observation channel, which they use for observing the environment, and 2 channels, a signal production channel and a signal comprehension channel, which they jointly use to communicate their beliefs. These are information channel, or in simple terms, probability transition matrices. I parameterize each of these channels with a single noise parameter, which is the probability of error, such that, for example, in the case of making an observation, the individual makes an observation with probability 1 minus eta, the correct observation is formed, and with probability eta, an error occurs in which a randomly chosen wrong observation occurs. But what is the dynamics of the model? In general, I assume that the population resides on a network. Here, a lattice is considered as an example. Each vertex represents an individual. At each time step, each individual with a probability H can make an observation of the environment using its observation channel, giving the individual access to a representation. In addition, the individual receives a set of signals from the neighbors on the network. The individuals comprehend the signal using their comprehension channel, giving them access to a set of representation received through communication. The individuals need to combine personal information and social information to form a belief, make an inference about the environmental state. For this purpose, I assume that the individuals use a noisy weighted majority rule in which the result of personal observation is weighted by a weight factor omega r, which is simply a self-confidence parameter. This is essentially a simple Boltzmann decision-making rule in which the individual form a belief A with a probability proportional to the Boltzmann weight of the belief. The weight of a belief is defined as simply as the number of times that a given belief or representation A occurs as a result of communication plus a weight factor omega r if that representation also occurs as a result of direct observation. So in simple terms, what is essential here, and the result depends on, is that this is simply a model of collective information acquisition where individuals live in uncertain environments. Individuals can make noisy observation of the environment and can communicate their information, giving them access to social information, and they need to combine social and personal information to infer the environmental state. It is possible to write down a set of mean field equations for the model, which govern the density of signals, the density of representations, and the density of beliefs. To write down these mean field equations, the mean field assumption is used, according to which the value of the variables can be replaced by their means. Using mean field equations in blue and simulations in red, I derived the bifurcation diagram of the model. In omega r, this was the self-confidence of the individual, eta C plane. This is noise in comprehension, in communication, in comprehension of the signals. The bifurcation diagram and phase diagram of the model are the same with respect to production noise. Also, the bifurcation diagram of the model in omega r beta plane. Beta is the weight, is the parameter of this Boltzmann decision-making rule plotted here. As you can see, the model shows different phases. For a large amount of noise in communication, disordered phase occurs in which consensus is not formed and individuals form independent beliefs. Consensus in which all the individuals form the same belief, more or less all the individuals form the same belief about the environmental state, is formed for a small amount of noise in communication. However, different consensus states are possible. For large omega r's, large self-confidence, such that the flow of information from the environment to the population is high, informed consensus occurs, in which consensus on the correct belief about the environmental states happen. For a smaller omega r self-confidence, the system becomes bistable. Another consensus, misinformed consensus, in which consensus on a wrong belief about the environment occurs, becomes stable, and the model becomes bistable, shown by IM here. For other values, for smaller self-confidence, multi-stable states are possible where disorder phase becomes stable as well. Similar monostable, bistable, or multi-stable states are observed in omega r beta plane. Given this rich phase diagram of the model, the interesting question arises that under what conditions and in what region of the phase diagram the population can make optimal use of information. To address this question, I assume that the population lives in an uncertain environment, in a fluctuating environment, where the environmental state changes after each t, here 100 time steps. In such a fluctuating environment, the individuals need to constantly update their belief collectively to respond to environmental change. Here, I color plot the inference capability of the population defined as the fraction of individuals who correctly infer the environmental state. In addition, the age of bistability, this line here, above which the system is monostable and below which misinformed consensus becomes stable as well and the system becomes bistable, is plotted. As you can see, the inference capability of the population is optimized exactly on the age of bistability. Here in panel A, noise in comprehension is considered, and in panel B, noise in production of signals, which shows that this result is valid for two different ways that noise are introduced into the model. In addition, we can see that a large amount of noise is actually non-detrimental as the population can still make optimal use of information and optimizes inference capability for a large amount of noise. A large amount of noise is actually necessary for optimal information use in a fast changing environment. You can see it here where the environmental duration time scale, the time scale after which the environmental state change is smaller than the previous case. In such a fast changing environment, the population can optimize its belief only for a large amount of noise in communication. So far, we have seen that the inference capability and the information use of a population in a fluctuating environment is optimized on an age of bistability, and noise can be beneficial for optimal information use. But how this happens? To see this, here I plot the fraction of informed individual in a fluctuating environment in which after each 50 time step, the environmental state changes. As you can see, when the environmental state changes, the fraction of informed individuals, those who correctly infer the environmental state, drops, and the population needs to update its belief. Three different noise levels are considered. For a small noise level, red, it can take a long time for the population to update its belief in response to environmental change, or it may even fail to do so in some cases. A large amount of noise increases the speed with which the population responds to environmental change, but it also decreases the accuracy as the fraction of informed individuals decreases in the stationary state. So there is a speed accuracy trade-off associated with noise, which is optimally solved exactly on an age of bistability, as we have seen through a phenomenon which resembles a stochastic resonance. This result is actually valid for different parameter values, for different parameters of the model, the different probabilities of observation, different amounts of noise in observation, or different environmental states, and also different networks, a fully connected network, a square lattice, and an Erdős-Renyi network are plotted here. So in conclusion, I have shown that a collective information acquisition system, or can be found in different phases. There can be different consensus phases, where correct consensus or a wrong consensus about the environmental state is formed. Also, we have seen that the use of information is optimized on an agent by stability, where both the trade-off between the use of social information and personal information and the speed accuracy trade-offs are optimally solved through a phenomenon which resembles stochastic resonance. This is reminiscent of some arguments that noise can be beneficial in biological systems, for example, by increasing the information processing capability of the population through stochastic resonance, or increasing the pace of evolution. Also, I have introduced two different ways where noise can be introduced into the model, which make the model suitable for modeling many biological communication systems, such as human language. And we have seen that our results are robust with respect to different ways that noise can be introduced into the model. However, these two different ways that noise can be introduced into the model, comprehension and production noise, can produce an asymmetry, which was not subject to my discussion here, between signal comprehension and production, which was subject to my other studies with my co-authors, according to which production noise can be more detrimental for the collective information acquisition of the population.
Okay.
Thank you very much.
Perfect in time. Okay, are there any questions in the chat? Let me see. We have some time for questions. People can also just raise the hand. Let me put all the people so I see if there are somebody making some sign. Okay. Let me see, I'm down in the chat. Okay, there are some comments. Just great work, thanks, very interesting. Okay, if there are no questions, I am going to put one just out of curiosity. When you present your phase diagram in the beginning, it does a mean field solution, right?
Yeah.
And then you talk about the same model into different configurations. How did you do that? By simulations? You talk about the networks, the agents in networks. This cannot. Yeah. So this is, I guess, not mean field. You made simulations out of it.
Yes. In the phase diagram that I showed, I had superimposed both the result of the mean field equation in blue and simulations in red. In my later graphs that I put the population in a fluctuating environment, I showed the result of simulations.
Okay. Okay. Thank you very much. Let me see if there is some of the questions. Okay, there are no more questions that I can see. Let me give a second more to people so they can think. Well, looks like no. So thank you very much. I am going to call the last speaker of this first part, which is Tuan Pham. Is Tuan there?
Yes, I'm here.
Oh, hello. Okay, great. So Tuan Pham is going to present joint work with Jan Kobel, Rudolf Hanel, and Stefan Turner. And they are people from different institutions. The section for the science of complex systems in the Medical University of Vienna, the Complexity Science Hub also in Vienna, and the Santa Fe Institute. And the work is a balanced triad formation explained by homophily-induced dyadic interactions. So again, 15 plus 5.
Yeah.
Go ahead.
So I can share my screen, right? Can you see my screen now?
Perfect, perfect.
So today I'm going to present my work on balance transformation explained by homophily-induced dyadic interaction. More than half a century ago, Heidegger came up with his fundamental insight about the so-called social balance theory. So in his theory, here you consider two different types of triangles in social network, which friendship and enmities. So if two people are linked, if two people are friends, they are linked by a positive link, which is j equal 1. And if they are enemies, they are linked by a negative link, which equal to -1. So Heidegger distinguished between so-called balanced and unbalanced triangle. So balanced triangle can happen if all the three agents are friends of each other, or if two of them are mutual friends, but they have the same enemies. So the second configuration of balanced triangle on the right here is correspond to the saying like the enemy of my enemies in my friends. And in the unbalanced configuration, you can have either one or three negative relationship. So this makes the triangle unbalanced. And for each of the unbalanced triangle, there is an associated social threat. And Heidegger has put forward the key hypothesis that inside a triangle, the social threat caused by the triadic interaction between individuals will essentially lead to the change in the polarity of the link inside an unbalanced triangle. So for example, the one on the left here is an unbalanced triangle, and one of the negative links should flip over to result in a balanced triangle. And similarly, for this configuration, if you have two positive and one negative links, so you have two ways to make the triangle balance by either flip one of the two positive links or flip the negative one over. And there is abundance of literature, empirical evidence supporting social balance theory. So almost 10 years, more than 10 years ago, like in his paper with collaborator, Cell considers a social network of massive online game Padus. So this is an online game in which player marks other player as their friends or enemies. And more or less at the same time, Les Kovac and his collaborator consider three large-scale online social network, so the opinions, Slashdot, and Wikipedia. And they commonly found that in all these four social networks, the number of balanced triangle, so the one with three positive link and one positive link here, the balanced triangle are dominant in the social network. They have a much larger number of balanced triangle in the social network and also in these three other social network. And you can simply introduce a measure of social balance. So the measure F here, which basically is the difference between the fraction of balanced triangle and unbalanced triangle. And the empirical value of F from across these four social network is like from 0.7 to 0.88. So it means that real social network is actually highly balanced. So not F not equal 1, meaning that it's perfectly balanced, all triangle are balanced, but relatively high level of balance exists in the network. So based on these observations, why are people interested in general social balance theory? So social balance theory has a very important consequence on the large scale organization of social network. namely that a social network which is driven by social balance tend to involve towards polarized or fragmented state. So by polarized state, I mean that, so I adopt one example from recent paper by RF and Wilson here, in which they consider the network of this US Congress. So the network between senators of the US Congress, and you see that there are two clusters, so left and right here, and inside the cluster, senator are linked by positive link, which is marked by green, and the link between two clusters are mostly negative. So red link here denote negative relationship. And for this network, we find that the F is also quite high and close to the one I showed for other network above. And in the previous slide. So this means that in general, if a network is highly balanced, it also have a high degree of polarization or fragmentation. So social balance, which is operated at the local level, right, in a group of 3 individuals, actually has a consequence on the global organization of the network at the global scale. So this is the main reason why many researchers are interested in social balance. And in particular, in physical literature, there are a lot of models which try to explain the emergence of social balance. One of such model is the model introduced by Marvel and his collaborator about in 2009. So starting from a Hamiltonian approach, they associate to each of the triangle an energy which is equal to the product of the 3 links inside a triangle, and then the total system energies, which is the global energy of the system, right? It's just a sum over all the triangle in the system. And so for positive triangle, for balanced triangle, the energy is negative, and for unbalanced triangle, the energy is positive. So because the way that the Hamiltonian specifies the dynamic is you at the 0 temperature, you try to minimize the energies, you try to get to the ground state, the lowest energy level of the system. It turns out that social balance emerge in this framework as the attractor of the dynamic. Yeah. And of course, that's it's also it had also been shown by Marvel and his collaborator that at 0 temperature there are abundance of so-called jump states. So those states in which your system get trapped into, and you have the energies which is not the global ground state, the global minimum of the energy level. But in general, this is a good picture. It's a way of physicists to formalize higher idea. And actually, not only this model, but many other work over the last decades on builds upon higher idea of the triadic interaction will drive a system towards the social balance state. So to the state in which there is a large number of balanced triangle and a very small fraction of unbalanced triangle can remain in the system. But in my work, this is ongoing work, it's not yet published yet, but in my work, I will try to give an alternative explanation for the emergence of social balance based on the dyadic pairwise interaction, but not on the triadic interaction between people in unbalanced triangle, inside triangles. So we start by considering opinions as a vector of binary components. So each of the individual in this network can be characterized by a vector Si here, and it has like a few number of opinions, the components. So for simplicity, we consider only binary components. So this means that you can have yes or no answer to a questionnaire, or voting for Trump or Biden, or choosing between two alternative companies, Apple or Microsoft. So just imagine that you have an individual with many opinions on different topics, and assume that these opinions on the topic are independent from each other. So there is no correlation between opinion on one topic to opinion on another topic. And based on that attribute vector, we start considering what is the effect of the attributes vector on the relationship between individuals. So we start by observing that there are two things which are important for determining the relationship. So the relationship between individuals essentially need to co-involve with the opinion. This means that whenever you update the opinion, you may also change your links with other. And another important principle in social network in general is so-called homophily. So by homophily, this means that people who are similar tend to become friends, and who are dissimilar tend to have a negative relationship. So that based on the homophily principle, we consider a rule, let's call it a rule. The rule is the links, it determines as the size of the scalar product between two opinion vectors. So I give here one example that you have two people, I and J, so they have their corresponding attribute vector, opinion vector, and then you calculate the similarity, the dot product between I and J, and you find that they are enemies. They should be enemies because the link between them have the value equal -1. And in this example, the number of opinions that I denote here by G's, variable G is equal to 5. But in general, we consider G's taking different value, odd value, not even value in general, because for the even case, for the case with even value of G's, you can have the type which we exclude from our consideration. And so if you know all the attribute vector of all the individual in the network, you can construct all the link between connected individual, right? And it's very important to remark that, as I showed you in the previous slide about the work of Marvel and on about how to explain social balance based on triadic interaction. All of these, most of the paper, most of the work using the same assumption, namely that they assume any agents can know the triangle, know all the triangle in their social neighborhood. So the assumption of this model means that I know the relationship between his neighbor K and J's, or between his neighbor L and J's. So this is some fundamental assumption in previous model of social balance. But I will consider very different setting. I will not assume that I know the relationship between his neighbor. So I do not have the access to that information. He just know his relationship with his direct neighbor based on the attribute vector. So this is quite different situation compared to the assumption of other model, and we will try to argue that even though the individual only know the relationship between him and other neighbors, we can define a model in which the equilibrium, the steady state of the dynamics is a social balance state. So let's see how can we do that. First, we introduce a so-called individual-based social stress. So we don't consider a global system energies Hamiltonian, but we make a localized version of that. So for each of the individual I associate to it a social stress I, which consists of two components. So the first part comes from the interaction between I and his friends. So some is restricted to the relationship between I and his friend, and the second part comes from the interaction between I and his enemy. So the interaction here is pairwise. There is no triadic triple interaction in that model, and we use a parameter alpha to gather the relative strength of the friendship to the enmities. This means that if alpha equal 1, people just care about their friends, and they don't care about their relationship with the enemies. And in the other extreme case, you don't care about your relationship with your friend, but you care only about the relationship towards your enemies. And alpha equal half is the most interesting case that we will focus on, because it seems that in that case you have an equal weight of the two factors.
Tuan, you have to start wrapping up.
Oh, sorry, I will just pick up now. So we will implement this model into 3 steps. We first pick our random agents, and then we flip it, one of its attributes, the one that I circle here, and then we calculate the change in the social stress between the after flip and before the flip. And then we use a metropolis algorithm to update the system state. So which means we have to introduce a Boltzmann factor, which beta is the inverse temperature. So beta have a social interpretation is an agent level of rationality. And then we get to this phase diagram of the steady state of the system, and we present here for 2 different number of opinions. You see clearly the transition between the unbalanced to the balanced phase. So the unbalanced phase, you have to measure F is very small, around 0.1, and in the balanced phase, the 0 region here, you have F equal 1. So this means that all triangle become balanced in this 0 region. And this means that there exists a critical value of beta C, beyond which the society become balanced. And another effect that we are looking into is how the number of opinion and the network mid-degree case affects the result. And again, we plot how the parameter depend on beta for different value of G's, and we observe that there is a scaling effect between beta C and G's. So actually, I don't plot it here, but beta C scaling as a power law of G with a power smaller than 1. But just from this picture, you can get that with increasing the number of opinion, you need also to increase the beta in order to get to the balance phase. And for another cases, when you just pick everything but change the degree of the network from very small to large, you will see that you decrease the critical beta. So this means that for denser network, beta should be smaller. And also the transition from the balance, from the unbalanced to balanced phases become sharper when you increase network mean degree. And we suspect that there may be some kind of transition from first order to from the second order transition to the first order transition up to some critical degrees. And another, so if you see from this previous picture that we have the transition from the unbalanced to the balanced phase. So it's in alignment with the social finding, empirical finding literature. But we want to understand what is the microscopic compositions of these phases. So how many triangles inside this balance phase? What are their fractions? So I just take a deeper look on the number of triangles of different types inside the balance phase. And I found that there is another transition that if you cross a critical value of alpha, you go from the case in which all triangle are of the type of plus 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 to the case in which the triangle that is dominated in the network is the one which 1 plus and 2 minus. So this is a topological transition. This is a transition between two attractors of the dynamic. And this feature happens if you cross some critical value of alpha. So it is the second interesting observation from the model. This dynamical phase transition can be somehow understood by looking at the additional order parameter, which is a fraction of friendly positive link. So you see that you have a transition of the own positive triangle here, but seem to be a critical value of alpha c equal 0.5. And correspondingly here, you in terms of the second order parameter rho plus, you also observe it because there must be a monotonic dependence between the fraction of own positive triangle and the fraction of positive links in the network. So this explains the previous phase transition you see in this figure. And the next thing we are looking at is what is the distribution of the cluster in the balance phase. And we look for different degree, network degree. So at the low value of beta, there can be very large cluster of, so the total size of system here is 10,000. And for beta small, a biggest cluster can take up 1/3 of the population. But when you have the beta higher, the distribution becomes a kind of exponentially distributed cluster. But for the network, but this is for k small. When you increase the k up to some value, you will see that there is a bimodal distribution of the cluster size, and the second peak of the distribution is around half of the system size. So the system size again is 10,000, and here at the point of 5,000, you see the second peak. This is quite interesting observation. So all the things that I present so far is only from the simulation of the model, but we managed to make one comparison between the model and the network of online player in the massive online game Padus. So if we calculate the cumulative distribution of which we obtained from the model, the blue curve here, and what is empirically found from the Padus data set, you will see that it's much quite well. It's not 100% reproduce the empirical curve, but qualitatively it's much together.
Juan, really is over.
Now I'm over. So I just quickly go through the conclusion. So the main message of the model is you can explain the emergence of social balance without using any triadic interaction. You can explain it based on homophilics by dyadic interaction, and then you observe two transitions in this model, one from the unbalanced to balanced phase at some critical value of beta c, and another transition which is topologically in nature, that you change this from one type of triangle to another type of triangle upon varying the second controlling parameter of the model, the alpha. And then the model seems to provide a correct statistic of the cluster size compared to what observed in empirical data. and there are some future direction that is I'm trying to calibrate the model with real data and somehow validate the model empirically, and also the model can be easily extend to like more general setting of hypergraph or multi-layer network. Thank you for your attention.
Okay, thank you very much. We really are out of complete the time, but there is, I'm gonna get to one question. Marioniso, you want to put it, please? Just one and quick answer. We cannot hear you. Maria Eunice, can you? Okay, well, looks like there is some problem. I am gonna read the question. By assuming that opinions can be described in terms of binary values, how does your model deal with opinions that cannot be expressed in binary ways, but might nevertheless affect the polarization and fragmentation?
It's a very good questions. But as you may see from the main structure of the model, what is important is way to determine the similarity between the two agents. So suppose that I can find a distance in the continuous space of opinion between two agent I and J's, I can generalize my model to that case as well. So of course, the choice of binary opinion is for just simplicity, but the model can be generalized for continuous opinion by modifying the expression here. Yeah.
Okay, thank you very much. Well, now we are about to, we should have got a break almost 10 minutes ago, but we are, I think we can make it. Let's stop for, let's say 10 minutes instead of 15, so we don't go so much. And we meet together. I mean, IC is having 37 at, let's say 45, we start again. So 5 minutes. So see you all at 45. Okay.
Good morning.
Hello, Ulrika.
Hi.
Do you want to try live?
Well, my internet did crash.
I cannot hear you. Maybe you are muted?
No.
No?
No?
I hear Laura, I hear you.
Yeah, it is
I
okay.
can hear, yes.
Hello,
I
hello?
also can hear.
Yeah, okay, wait a second. It's my fault. Now I can hear you.
Okay,
Yes.
better.
So my internet, unfortunately, there's an engineer coming out today to fix the internet, but only after this is over. So it did crash once in the previous session. I lost connection, but it was only for about a minute or so. I don't know, it's your call. Now I can't hear you. No, nothing.
Either, Laura.
No, no.
Now?
Yes.
Yes.
Yes. Now it's...
I must have touched it by mistake. Okay. I don't know what to tell you. It crashed recently.
Well, in the previous session, I once lost connectivity, but it was for about a minute. Like it wouldn't have completely destroyed the.
Okay, if you prefer live, we can try live. I understand it.
I mean, what's your intuition? It's.
I don't know.
It's not ideal.
Network.
It's
okay.
Let's go live. It's always better.
Yes.
Okay, well let's just
yes.
let's just try live and hoping that if I lose connectivity, it probably won't be long.
Mm-hmm. In
Yes,
the
yes.
worst case,
Wait
we
for-
have to delay a little bit. I have the video, so I have to catch up
That's
more or less
right.
where you are and try to
You
see
can find
how-
exactly.
how
Let's try
good.
then. Okay.
Okay, so let me see if everybody's back. I'm not sure. Okay. But it's more what we said. Okay, so now we're gonna go to the last part of our session. And I am very, very happy to introduce Professor Ulrike Hang. She's professor of psychology in the Department of Psychological Sciences at the Birkbeck University of London. She's also director for the Center for Cognition, Computation and Modeling. And he has a lot of work contributing on cognitive science, argumentation, language acquisition, and she's gonna talk about the nature of testimony. And Ulrike, I let you the ground. As you know, I'm disappearing and I am appearing 3 minutes before the 40 minutes are gone. Okay.
Okay. Thank you very much.
Not at all.
So I'm going to try to convince you today that we're probably all much more vulnerable to misinformation than we might think. And I think the way we can see that comes from thinking about the very nature, the very fundamental nature of testimony. So testimony is just the fact that we receive information from others via communication. And philosophers, legal scholars, psychologists have concerned themselves with the problem of testimony for centuries, really. And the issue, of course, is how can testimony from others lead to accurate beliefs, given that even our most reliable and well-intentioned people are not going to be 100% reliable. And the question is, what follows from this for our beliefs about the world? Now, what I want to focus on in this talk today are two aspects of testimony that I think have been overlooked historically. While it's clear, on the one hand, that we have to somehow factor into our belief revision and knowledge acquisition the fact that our sources won't likely be perfectly reliable, there is a fundamental problem that I think has been overlooked, is that we also typically don't know the true reliability of our sources. So I'm going to say something about that. But then there's another even more overlooked problem, which is that testimonial evidence isn't just a matter of single sources, but of course happens across wider social networks. And it might, of course, be bizarre at a network conference to suggest that there's things that we don't know here, particularly given that there have been decades and decades of research, not just on opinion dynamics in group psychology, but of course, there's been a huge amount of modeling of opinion dynamics across social networks. But crucially, much of that modeling has taken approaches such as a social physics perspective or considerations of opinion as contagion that mean that it doesn't really tell us much about the accuracy of our beliefs, which is what you're interested in if you're interested in knowledge and misinformation, right? Opinions are not beliefs about facts. And to understand what's going on with respect to facts, we need a modeling context minimally where there's some kind of ground truth. We can't just be content with looking at whether a consensus forms or not. We have to be able to see whether that comes up with the right answer or not. And of course, there's been work on that too. And there's ever more work on that, but it's much, much smaller in volume than other things. So in this talk, I'm going to talk about these two seemingly separate problems, which I will then also try to convince you unfortunately connect in ways that are not good for the accuracy of our beliefs. So I'll start with the first one, the problem that we typically don't know the true reliability of our sources. So it's clear when we get evidence from others that we should normatively factor in the fact that they're less than fully reliable, even if they're well-intentioned, right? So Laura tells me something, I should revise my beliefs in light of what Laura's told me, but I should also normatively, presumably make some allowance for the fact that people like other data sources in the world can be less than 100% accurate. But the question is like, what particular degree of reliability should I assign to Laura, right? Well, so one strategy that I can have is I could just assume a particular degree of reliability or accuracy for unknown sources, right? Like simply assume, for example, that they're moderately likely to be right in confirming or rejecting a hypothesis with probability 0.66. I'm going to call such a strategy fixed trust, right? You assign a likelihood in Bayesian terms, and you just stick with that. Or I could try to estimate reliability and also do that dynamically over time on the basis of past success, where I have access to a history of statements or predictions from a particular source. I can use that to form a reference class. I can look at the proportion of things that turned out to be true and use that as an estimator for the reliability of that source. And there are well-known Bayesian procedures for doing that kind of thing. But of course, that requires that I have access to outcomes of past statements. And there will be context in which I don't have that for a number of reasons. And in fact, there will be quite a few contexts. One is that I might be dealing with a familiar source, but they're now just talking about something new that seems unrelated domain-wise to what they spoke about previously. And I don't just want to carry across their expertise. Imagine a friend whom you talk about football with all the time. You know that person's very knowledgeable about football, but now they're talking about vaccines. And you think, hang on, just because somebody knows a lot about vaccines, football doesn't mean they know something about vaccines. You could also be talking to somebody for the first time. You might not even know who the source is if you think about online social media. And of course, people could be speaking about unique events for which it's hard to, single events, for which by definition, there isn't any past reference class. So in those circumstances, what could I do to estimate the reliability of sources? Well, one thing you could do, and I think people arguably do, is that you try to estimate the reliability of a source based on the plausibility of their testimony. So you're doing something like this. You're basically making, if I think of this in a sort of Bayesian terms, you're making a joint inference over the reliability of the source and the claim at issue. Or more informally, what you're doing is you're using your present uncertain degree of belief in the claim to adjust your belief about the reliability of the evidence reporting source. So if Laura says to me, Ulrike, the Earth is flat, what I do is I revise upward my belief in a flat Earth. But because I'm presently quite convinced that the Earth is not indeed flat, I also downward revise Laura's reliability. And so in that sense, a history of interaction with a source, I'm using this mismatch between my current belief in a hypothesis and how expected the evidence is that the person is giving to revise both my beliefs about the reliability of the source and the truth or falsity of the claim. And because of this is targeted not to past outcomes, but to current expectation, we've called this strategy expectation-based updating. And I've spent much of the last 5 years thinking about this strategy in one way or the other. So one thing we've done is that we've run a number of studies and produced a number of articles that show that people use this kind of strategy or seem to use this kind of strategy in lab-based context where they're given information from sources. They seem to spontaneously revise their estimates of the reliability of the source. I've also looked quite a bit at how you could implement such a strategy. There are different formal models of source reliability that all take this same fundamental intuition across different parts of philosophy and psychology. And there's differences in detail, but for the purposes of the talk, what really matters is that the fundamental feature that's the same. And then of course, I've been particularly interested in whether that's actually a good or smart thing to do. So in this topics paper, 2018, we started to look in detail through simulations at the performance of this kind of strategy. And I want to start out by telling you some of these results. So what we can do in these simulations is that we're going to have an agent who receives evidence from the world. The agent in both cases is a Bayesian agent trying to do the best they can. They're going to receive probabilistically evidence from the world about the truth or falsity of a single claim. And they're going to use Bayes' rule to update their beliefs given that evidence. And they're going to get 10 trials of evidence. And we're going to vary across runs of the model the objective quality of the evidence, that is the true likelihoods. And we're going to contrast, in order to understand the features of this strategy, this kind of expectation-based updating agent with a fixed trust agent who starts with the same degree of initial trust and just retains it. And the particular update agent we're looking at is one that an implementation that comes from Eric Olson at Lund University. And this is a normal Bayesian agent, but the likelihoods, for the reliability, this agent has a beta distribution over possible likelihoods, and these are revised dynamically after each piece of evidence. So what happens when both of these agents face a single generating data source over 10 trials rerun many times? So there's going to be 1,000 simulations of these 10 trials for each of the data points I'm going to show you. So the first thing you should see when you look at this graph is that we have here the expectation-based updating agent and here the fixed trust agent. And the first thing you should see in this plot is that they look virtually the same, even before I tell you what they are in detail. So what they are in detail is that on the y-axis here, we're showing the posterior degree of belief on average in these agents. Across, for the z-axis, different base rates at which the hypothesis is true or false. Agents in these simulations, I should say, don't have access to the base rate. They start with an uninformative prior of 0.5. And then we're varying along the x-axis here, the quality, the objective quality of the underlying evidence, which ranges all the way from the evidence is always correct to it's like flipping a coin at 0.5 to being a systematic liar at 0. So what we see here, first instance, is that there's almost no difference discernible with the naked eye in the posterior degrees of belief that these two types of agents generate in this situation. So I'm going to collapse across the z-axis, the base rate dimension, because it's not really doing anything here, and talk you through what these results mean in a little bit more detail. So it might seem counterintuitive, and it certainly did to me when I first saw these results, that these two very different strategies should behave so similarly. And you might wonder whether this is some feature of the particular parameters we we chose or what this is or whether, but I think what I can convince you is that this actually reflects not something specific about the models and their implementation, but a deep characteristic of the problem. And the way to see this is to think about this range of objective likelihoods, the possible quality of the data. On the y-axis now is squared difference from the truth. That is an error measure, not posterior degree of belief, but otherwise things are the same. And if we think about the quality, the underlying quality of the evidence, we can think conceptually that there's like 3 distinct zones. There is this kind of green zone here where the data are highly reliable. And in that case, any model, right, that has the right assumption about the qualitative direction of the data will, given enough data, learn the truth about the world. And there are mathematical convergence results that show us that that's the case. So there's not going to be any real difference here between the expectation-based updating and the fixed trust agent. And then there's this intermediate zone where the data are so noisy as to be virtually worthless. In that case, of course, no agent can learn, and that includes an optimal agent, optimal Bayesian agent who knows the true likelihoods, right? Here at 0.5, the data aren't telling you anything, there's nothing to learn. So again, the 2 models aren't really going to be distinct. And the one where we might have hoped that expectation-based updating would help is in this world here, where the data is basically lying. The data are systematically mislabeled or consistently wrong. At 0, there's a consistent signal, but it's always saying no when it should be saying yes with respect to the truth or falsity of the hypothesis. But of course, the problem here for these update agents is that they have to start out trusting, right? Otherwise, you can't learn anything from a source that you think doesn't have anything to say to you. So they'll receive their first pieces of evidence. They'll come to form a positive initial assessment early on of the truth of the hypothesis. And then all of the evidence that they get will just be congruent with that, right? Because they can't step outside and just look directly at the world, right? All they have is the consistency of the data stream. And if that data stream is consistent and you believe the person, then you're just going to end up maximally wrong on any model. So really, arguably, I think any learning model you could have that has access only to the information these models have is going to end up with the same profile. And this is important, I think, because it shows us that there is a limit to how much adjusting our beliefs about the reliability of a source is actually going to be helpful. What really matters is whether we are right about whether a source is indicating evidence for or indicating evidence against a hypothesis. But after that, a lot of it is not going to make much of a difference, particularly in a world where we then get lots of data. And that might be counterintuitive. It certainly was to me. So that's the first problem. The second problem is that testimonial evidence isn't just a matter of single sources, but of course happens across wider social networks. And this problem is going to turn out to be connected to the one that I've just shown you. So on to this one. Well, we already know, and it should have come as a surprise to exactly no one, that network structure will affect the accuracy of people's beliefs. So we know that from behavioral experiments. It was to be expected on the basis of simulations of opinion dynamics. And we can also see this now in agent-based models that put agents of the type that I've just outlined, these expectation-based updating agents, in a simulated world where there's a ground truth. Now, in that world, we have agents who receive both personal information from the world and social information via the testimony of others. There is a single proposition that's at stake, and they start to receive evidence from the world. And once their beliefs exceed a certain degree, a threshold of assertion is passed, and they're then also, when queried, willing to report to other agents that the proposition in question is true or false. And on any given run, it's stochastic, there's a probability that you get evidence from the world, there's a probability of communication, and all these are parameters in the model. Using that kind of basic setup, you can show that you get differences In the accuracy, again, here on the y-axis, is an error score, the mean average belief in the network across different network topologies. And in some ways, that's not surprising at all. What's maybe a little bit more surprising is that you can get differences in accuracy even for networks that have exactly the same number of nodes and exactly the same number of links. And that's important because it gives us a sort of first clue that there's more going on here than just the fact that, of course, what you're doing when you're sharing information is that, you know, the more you share, the more information there will be. So you would expect accuracy differences. Even if I equate how much information is being shared, I can get impacts, seams of topology on accuracy. So one thing I could do in this context is I can start to drill down into network features. I can look at standard metrics of topology and try to work out what's driving those effects. That we do some of that in the paper I've listed here, but that's not what I want to do in this talk. Rather, I want to carry on and show you two more general systems level properties that I think are illuminating. So the first one is overconfidence. Overconfidence is a phenomenon that people in the judgment and decision-making literature, also behavioral economists and meteorologists, any kind of forecasters have long been concerned with. And it concerns the relationship between objective probabilities and subjective probabilities. We can imagine a range of objective probabilities and an agent's subjective estimates thereof. If the subjective probabilities perfectly match the objective probabilities, that is, the agent is calibrated, then all the estimates will lie on this blue diagonal line. For an overconfident decision maker, for an overconfident forecaster, the subjective probabilities are more extreme than the objective probabilities, right? So the objective probability might be 0.3 and the agent says 0.2. Or it might be 0.75 and the agent says 0.8 or 0.9. And that matters, and that's a concern because overconfidence is a systematic bias that will lead to particular types of poor decisions in certain contexts. So this is something we kind of care about. So what I want to look at is the question of how these strategies that I've talked about so far and communication across social networks impact overconfidence. Overconfidence is hard to study in a social network context because it's very hard to track for an individual agent what degree of belief they normatively ideally should have had. But there's a simple trick that we can use to study this at a population level. Because when we have a population of Bayesian agents, some of which who will receive positive evidence, some will receive negative evidence about the world, Bayes' rule makes it the case that if those agents start out knowing the true base rate, then even though beliefs will go in different directions depending on the evidence that people in this population stochastically receive, at the population level, the population will remain calibrated. So we can look at deviations from calibration at this population level to get a sense of what's going on. So this is exactly what we did. Use now the same model of these expectation-based updating agents, the fixed trust agents, and in this simulated world that I already told you about. So this is what we find. So first we have the updating agents and the fixed trust agents. And these are called shadow agents because they're just individual agents that aren't participating in communication. And the name comes from the fact that the way we run the simulations is that we have a simulated network and each node in that network has a direct copy, i.e. a shadow agent, who receives all the evidence from the world, all of the personal information that that agent gets, but doesn't participate in the communication. And that manipulation obviously allows us to factor out the effects of network communication from the influence of the data coming from the world. So I've oriented the same landscape plots as before, but now in a way such as that they match this overconfidence plot, right? So we have the prior, which equals the base rate. These agents now start out with the true base rate. So this is your objective probability. And this is the average average belief in the population across many runs. This is your subjective probability. So if these agents are entirely calibrated, then all posterior degrees of belief should lie on this diagonal straight line. And the first thing we see is that they don't entirely. For these updating agents, there are hints of overconfidence at high levels of evidence quality. So I should say the z-axis, again, is the objective likelihood, the true reliability of the data generating source. Then the evidence coming in from the world now just in the range from random coin flip to 1. And this doesn't look like much, but that is already real overconfidence. But the real question is what happens when we put in communication? And when we look at communication, we now get considerable degrees of overconfidence in both the fixed trust agent and the updating agent. And what's even more worrying about this degree of overconfidence is that the overconfidence gets worse the lower quality the evidence coming in from the world as we move to lower and lower objective likelihoods, closer and closer to a random coin, the degree of overconfidence increases, which is the opposite of what you would hope to see, and is actually kind of quite concerning. So why does this happen? Well, we've got two things going on here. At the level of the individual agents, we get overconfidence because this expectation-based updating provides a kind of amplifying ratchet for the subjective weight of the evidence. If I get a sequence of positive reports from a single source that all fit with my beliefs, I keep increasing my the subjective trust or reliability of that agent, which means that each subsequent piece of evidence, I'm giving greater evidential weight. So this is why overconfidence is not surprising, and also that overconfidence would be greater when objective likelihoods are high, because that is where you're more likely to get a consistent data stream. But what's going on at the network level? Well, at the network level, the key driver of what's going on is that agents must assume independence of sources for computational reasons. So these are all Bayesian agents, but they're naive Bayesian agents who assume that the social information they're receiving from others is independent, when in fact it isn't, because everybody's part of this wider social network. And there's a deep reason for that. Not only is this realistic, because in the real world, we have no way of knowing what the connectivity, the topology is of the wider social network that we have, but for computational reasons, even if I do know this social structure, in the context of my simulations, I can't computationally actually make use of this for purely computational reasons. So you have to make this independence assumption. And while naive Bayesian agents who make these independence assumptions do well in many contexts, and they arguably do well here too, this does give rise to a very particular kind of bias that we're seeing. So this already is a further reason why your beliefs will be wrong to a certain extent, right? Why we can't individually guarantee the accuracy fully of our beliefs, because this social network context and its structure is completely beyond our individual control. And we see the impacts of this overconfidence also in patterns of belief convergence over time. Just as a quick illustration, these are sort of sample runs of time course over subsequent time steps of the model. So the agents here, these are agents that are starting out with a degree of belief 0.5, just for illustrative purposes. But we see agents who are participating in communication in red, and agents with shadow agents with no communication in blue. These are updating agents in both cases. And we see that the communication is positive and that it leads to more information, so faster convergence. And it does so in a way that typically goes in the right direction. So we can see that with this contrast with this green agent, who you can think of as an ideal Bayesian agent who simply gets all the data coming from the world, all of the personal information, and just directly updates on that. So this agent is basically going to go in the direction of the truth in the simulation. But the worrying thing is that occasionally we see that an entire population of these expectation-based updating agents will converge faster than the ideal agent, right? Which shows us that, strictly speaking, the reduplication of evidence in the network, the fact that there's a kind of double counting that can happen as violation of independence, means that the network as a whole behaves as if there's more evidence from the world than there actually is. And this is why we can see overconfidence. But there's another feature that goes with this. So one of the other characteristics of this model that had already been kind of pointed out before is that while most of the time, the agents in this simulation, when the evidence is even moderately diagnostic, coming from the world, will end up with the true belief about the world, you do get runs where the majority ends up completely convinced of the truth of what happens to actually be true. But there's a small minority of conspiracy theorists, basically, of crackpots, who are totally convinced of the opposite. So one of the things we were also interested in exploring is what happens to the proportion of these conspiracy theories. These are the people who've become, or look like they've become, subject to misinformation, right? Well, they have become subject to misinformation, but of course, they're just like everybody else. They're all agents who are trying to maximize the accuracy of their beliefs. They don't have any particular bias. They just have an unlucky evidential history or record. So what about the kind of relative proportions of these, and how often does this kind of split emerge? How often are there these kind of crackpot misinformation people, even in these benign circumstances? So the particular metric of polarization we're looking at is extreme divergence, right? So we're scoring as polarized a society, a population in which there are agents who are completely convinced in the truth of the proposition at issue and agents who are completely convinced that it's false. So there are some agents who are maximally separated. I mean, they can compare this for these update agents and the fixed trust agents. And again, we can compare against the network and the no network context. And on my y-axis here now is just simply the proportion of societies in a large scale simulation that have such a split. And the first thing we see is that that there's differences as a result of the quality of the objective evidence going in, and those fit with what I showed you about overconfidence. The worse the evidence coming in from the world, the more likely people are going to end up in radically different bits. The next thing we see is that there is a negative effect of this expectation-based updating strategy, which at this point should now not surprise you, that there's clearly more polarization in those societies than there is for the fixed trust agent societies. And there's also an effect of communication. There's always more polarization in the networks than there is for the respective shadow agents. I'm going to draw your attention to this here, that the fixed trust agents in this particular simulation, where we let it start at everybody at 0.5, again with an uninformative prior, show no polarization of this kind at all. And that is interesting because that also opens the way to identifying another effect, which is that actually this polarization gets worse as we make the network bigger. And that's not just a sort of simple size effect where you think, okay, I've got a bigger pool of people, so it's more likely that there's going to be a random crackpot there somewhere, because even as we make the networks larger, go from 60 nodes to 90 nodes, we never are getting any polarization in these shadow fixed trust agent societies, but we're getting more and more polarization in all other conditions. So again, we can see in this model how you can be epistemically unlucky. You can become subject to misinformation for reasons entirely beyond your control, and moderated by factors such as the size of the network that also are entirely beyond your control. And final slide, just to show you that these results are robust. This is an even larger set of simulations. Here, this looks at all network sizes from 0 to 100 nodes. This row is the updating agents. These are the fixed trust agents. And these are now different topologies as well, where we're varying from a small world network to an almost random network by changing the rewiring parameter for generating a small world network. I should have said, I didn't, I think that the vast majority of simulations, all of the ones where I didn't give a structure, are using small world networks. And so we can see there's a really robust effect of network size here. So what does this all mean? I think what this all means is that we think about the nature of receiving information from others and the impact this has on the accuracy of our beliefs. That is when we think about the problem of testimony and we look at these two, I think, typically overlooked problems, that we don't know the reliability of our sources and that this happens across wider social networks, then I think what we see are limits on the extent to which we ourselves can successfully accommodate the fact that others are less than fully reliable. And that means, I think, that we're much more at the mercy of our information environments than we might like to think of ourselves as being. I think we think of ourselves as sort of dodging and weaving and trying to, distinguish good sources from bad sources. And we're inclined to believe that that has a sort of huge effect on how accurate our beliefs are. But I think these simulations give some reason for seeing that there's going to be kind of hard limits to how effective that actually is, right? I think closer consideration of both of these features that I talked about reveals, I think, that the accuracy of our beliefs is much less under our own individual control than we would like to believe. So to wrap, I think I've showed you that overconfidence can be a natural outcome of communication across social networks. Likewise, that polarization can be a consequence of this expectation-based updating and network size, where expectation-based updating is just a strategy that I think people actually use, doesn't just seem intuitive. I think people actually use it, and we have evidence to that effect for trying to estimate the reliability of our sources. And by doing all of this with Bayesian agents and trying to build optimal agents that try to deal with these problems, I think we're able to reveal that these problems are actually deep-rooted, right? This is not just a sort of mere feature of the kind of agent that we've chosen. It's these agents are as good as you could conceivably be, and they're still kind of running into problems, because these problems, what that's telling us is that these problems are actually deep. And I think that has implications for any attempt to kind of fix our current information crisis, right? In that any true or deep fix must also ultimately address whatever problems these optimal agents face, right? If much of the problem is coming from these kind of deep structural things, then just having media literacy classes, however useful or well-intentioned, isn't going to be enough to fix the
Okay, it was going well, but something happened. Let's get a second to see. I sent a message and I'm waiting to see if she realizes. Okay, yeah, that's good. I don't see her. Is she connected or not?
No, she's not.
No, she's not. I was trying to see if she's not in the waiting room either, because I should see that. Okay. Okay, at some point I can try to see where we are in the presentation. I think she was almost by the end. I'm looking at her video. Yes, she was almost over.
Yeah, it seems that she was wrapping up.
No, she was on her last slide. Okay, I'm just. I have her video because we knew this could happen. It was it's her before last slide. So, but it's very, very sad if she cannot reconnect, because I guess there must be questions.
Eventually, you can put the last part of the video.
There is no last part of the video. It was the really it was the last transparency, and then she has to announce her co-workers. It's really the last one. So what we are missing the questions, and I think it's a pity.
Eventually, we can put the next presentation and do the questions.
Yes, I will do that. I was just waiting just for politeness. 5 minutes, because she should. She didn't use all her time. So she's almost now. She's about to finish the talk. She should be finishing the talk in 1 minute, and it's still time for questions. So I think we can wait. I'm just monitoring. I guess that I should see her if she tries to enter again. It's a pity I don't have a way to contact her directly. I'm trying by mail. Okay, well. I don't know if she has the app in her phone. Maybe we can contact her and say just connect. Okay. Okay, what I propose is just to, I'm gonna let her a message and say that we can pass the question after the next talk, because we still have 5 minutes. But maybe instead of losing them, we can advance the next talk and eventually give a place for questions after that one. So. Okay, yeah, no, she's not. Okay, I just try to put a message for her in case she comes back, not to be surprised, but you cannot if she's not on. Okay, well, okay. Let me send that by email, and let's hope that she's gonna see that. In the meantime, I am calling Tiago Santos. So
yes, I'm already around. Can you hear me?
okay. Yes. Just give me 1 second. So I send a mail because I don't want her to be cut like this.
Okay.
Okay. So let's go. The new speaker, the next speaker is Tiago Santos. This is a joint work with Jorge Lousa and I don't know the first name, Coelho. This is a joint work at the Department of Information Science and Technology at the Instituto Universitario de Lisboa, Lisbon, and Portugal, and in the Department of Informatics of the Faculty of Sciences at the same University of Lisbon, Portugal. And the title is Agenda Setting Effects on Twitter Brazilian Presidential Elections in 2018. So again, 20 minutes, 15 plus 5.
Okay, let me share my screen with you. Okay, thank you, Laura, for the presentation. Too bad we didn't have time for some questions. For Ulrike, let us hope that we have some time next. I promise that I'll be quick.
No, don't worry.
My work is on agenda settings effects on Twitter in Brazilian presidential elections of 2018. Some colleagues, Brazilian colleagues, already seen this presentation, so I apologize for the duplication. But here it goes. As Laura said, this is a joint work of me with Jorge Lousa, and Elder Coelho, which are my PhD supervisors. Okay, I'll start with a very straightforward definition of what is agenda setting theory. Agenda setting basically departs from a very simple principle that if you are not in contact with political actors, then you can only know about their political agenda to the media. Then this gives the power to the media to transfer their political agenda per se to the audience or the citizens in this case. This theory is around since the 70s. It used to be done normal with inquiries and interviews. Basically, researchers would find out what the papers or the media were publishing, what kind of political issues were publishing, and then they will compare them with what the political issues that the citizens have in their minds, and then they if those two matched, then we could say that was success in the transfer of the political agenda from the media to the citizens. Right now, and with social media and Twitter and all those social networks, and the internet itself, this work is much more, it can be much more massive, because you have a lot of data to work on, and you can have much more general overview what is going on, because social networks, in this case Twitter, is open to the public. We can make this kind of research and have an overview, at least what is going on. So in this case, this is a second case study. We already have a case study also around, about the Brexit elections. In these case studies, we are trying to find out what are at least on Twitter, what are the media that are successful in transferring their agenda to the public. In terms of methodology, we grab the tweets with the Twitter API. We search upon a pre-selected set of keywords that were related to the elections. And we have here an example. We got a tweet from Folha de São Paulo that has a link to Folha de São Paulo, and then we crawled that article from the newspaper, from the website of the newspaper. This gave us three sets of corpus. The first corpus has the tweets themselves. The second has the title of the article, and the third one has the text of the article. Later, we did a topic modeling upon this with latent dirichlet allocation, and which gives us a set of vectors, and upon these vectors we calculated the distance between them with or the similarity between them with Euclidean distance, which is a pretty used measure. Regarding the sample, we have about more than 4 million tweets from an interval of 4 days before the election. More than 500,000 of unique links, and from 3,016 domains. We also did bot detection. We have to thank here our dear colleague Filippo, because I used the Botometers trained data sets. We first selected the users with more than 200 tweets in this interval. It was 4 days. We think there's a good start, and with the model that we created, we found out that 87% of them were in fact bots. This model used an AdaBoost classifier and Smoothie and the NN, and we got a precision of 100% on the training set and almost 100 on the test set. Regarding this sample, regarding the content that we detected that was published by bots, we saw that 12% of it, 12% of the total sample size was generated by bots. This is more or less with the literature that says that about 15% what is going on social networks is published by bots. And this is interesting because only 0.2% of the users generated almost 12, more than 12% of the content, and 20% of the unique shared links, and 14% of the domains. Regarding the top media, we only analyzed the top 20 for the sake of feasibility. We saw that on these top 20, 10 are traditional, but the other 10 are not traditional, and they include partisan, emerging media, and also a fact-checking site. This is something new to the web ecosphere, or the new media ecosphere, because previously, before the internet and social media, it was very difficult for emerging media or partisan media to have this kind of exposure, and right now with the internet you can do it. This is the 10-20. Regarding the bots, we see more or less the same tendency with the first three ones, Folha de São Paulo, Globo, and o Antagonista. What we can see here is that mostly emerging and partisan media have their presence generated by bots, which you see the numbers on red. Which makes sense if you are an emerging or a partisan media and you are not so institutionalized like the traditional media. It's normal that you use it should not be normal, but you can infer that they are using some kind of automation to stay on top of mind of the users on Twitter. This is the 1020. And the first set of experiments that we did, we grouped the media according to the number of tweets that had links to their web pages, and we've got this nice curve, and we saw, whoa, this must be some kind of a power wall, which it turns out it is a truncated power wall. And we infer here, according to the context of this power wall, that must be some kind of preferential attachment dynamic, which is the traditional on the web, which is the rich gets richer, which explains why traditional media are here on the top. But we also think that might be some kind of maximum entropy dynamics, attachment dynamics, because the presence of emerging and partisan media, which by using bots, they generate their movements, they increase their movement, and this movement leads that users tend to relate to them in some way. So we think that might be these kinds of dynamics that construct this nice power wall. After that, we already on the similarity between the different corpus, we first did this experiment where we compared the difference between the tweets and the titles of the articles. And generally speaking, we see that the bots tend to be closer to the media message, which is something that makes sense, because bots imply some kind of automation, and normally this is automation concerns the sharing of the articles of the newspaper. So it's normal that they share more or less the title that is on the web page. We see that the most disputed, and when I say disputed here, I say the ones that have more difference. I'm not implying some kind of polarization. I'm only saying that what people were saying were different, that on the tweet was different that was on the title. And we didn't make any kind of sentiment analysis on here. And we see that traditional media, and here Folha de São Paulo and Globo, are more disputed in this sense than the rest of the other media. And the less disputed were the fact-checking and the Terça Livre, which is a partisan site, which makes sense because normally partisan sites have a more faithful audience, and also fact-checking tend to reproduce and try to recur to fact-checking as ground, some kind of ground truth, and so it's normal that is not being disputed. They are not being disputed here. On the next set of experiments, we calculated the previous experiment with the blue line. And then we did another experiment where we calculated the distance between the tweets and the text of the articles, and the titles and the text of the articles on red, green and red respectively. We found out that the titles are closer than the text, which is normal, because the morphology of the tweet follows more or less the same lines of the articles. It's more or less 240 characters, which is similar to the title of a web page or an article, a news article. But then we see that there is a correlation between the article titles and the text in the tweets, which which we understand this has a measure of the media success in transferring their agenda to the public. If the tweets of the text somehow correlate, if the tweets somehow correlate with the text, then we can say, according to agenda setting theory, that that was success on their transfer to the media. We speak generally, but individually we can see that there are differences, and again, the differences are the same that we observed previously, that most traditional media are being more disputed than the emerging and partisan media here. After that, we did another. This is the same experiment to the regarding bots, and here it follows more or less the same tendency, but we don't have a correlation here, which also we think that might make sense, because if you are trying to, if you are recurring to some kind of automation, is because you want to pass another a message different than the message of the traditional media, at least, and it is normal that by doing so you end up passing a different message than traditional media and the other media were passing. On this experiment, we grabbed all the tweets, and when I say all the tweets are the more than 4 million, and with the links and without links, the normal conversation between the users, and we compare them with the tweets of the media. This is the tweets that have links to media, to their titles and to their text body, and this result was a bit surprising, because we were waiting that or expecting that the titles would be more similar to the general opinion, because it was the first thing that we discovered on the first set. The set of experiments, but no, this is the text that is closer to the general opinion, which also makes kind of sense, because they were correlated previously. But either way, we think that might be in place some kind of complex opinion building dynamic, because and we hypothesize that what the users are reading about the media ends up more or less on the tweets. Okay, this is the equilibrium distance also for the last experiment, but for the corpus of bots, and it follows more or less the same tendency. And finally, we did this experiment where we calculated the entropy to the corpus regarding the media titles, text, and body, and we did the same for the corpus of bots. And we see here that is generally a drop in entropy. The bots generally have less entropy, or the speech that the bots are automating generally has less entropy, which is also that also makes sense. If you want to spread some kind of message, and if you are automating that message, is normal that you are passing less information by doing so, which is kind of problematic if you think that 15% of the content is generated by bots. You are saying that this leads that the conversation on social media is generally poor in some sense because of this. And in concluding, we saw that the distribution of the media, we found that the presence of preferential and maximum entropy attachment dynamics. Traditional media here did not dominate the debates, as alternative media played an important role on the campaign, which is something that we also found out for the Brexit campaign. The media, but even so, the media were successful in transferring their agenda to the public. And in terms of metrics, we found that the titles of the articles are closer to the tweets, but in the overall opinion on the data set, we found out that the text is more representative. We also saw that the emerging and partisan media tend to have a more significant share of their presence generated by bots. And this is I think this is a way to challenge the position of traditional media. And finally, these bots generally generated a less entropic and informative and more poor speech or debates. We are thinking about the implications of this in terms of in political terms and policy making. Some kinds of this we call them recommendations here are in line with some things that Filippo mentioned on his presentation. We are watching this, but this kind of ecosystem that is growing up on the social networks is something that is not separated what the monopoly of big tech companies have, and therefore we think that we must have some kind of transnational regulation in order to regulate this speech on the internet and on social networks. We know the European Union is working on the Digital Services Act. Recently, also in the United States, we have some antitrust laws trying to be passed. So I think the governments are more or less aware of this, but we still think that there is a big way. Until we reach this place. We think also that there must be the creation of standards of development of digital platforms, so they can be audited by public entities. As researchers, we have a lot of difficulty to understand what's going on, and Filippo mentioned some issues. And we also need the availability of open and consistent APIs. And also what Filippo mentioned, at least on Twitter, we must reduce the rate limits. Right now, if I'm not mistaken, is 300 tweets per hour, which someone with a minimum knowledge of Python or whatever language can do this, and we think this is not acceptable, especially when the speech on social networks has the implication on our real lives and on societies. And finally, and we think this is very important, there must be some kind of alternative and decentralized public services that can ensure some healthy competitions with ensuring the private offer. If we are seeing the digitalization of a lot of services, what the first example that comes to mind is the postal service. Right now is mostly email, and at least in Portugal, and there is a public service of email, but on the internet you don't have any kind of public service of email, at least not in Portugal. So governments, and we think that governments also must be aware of this and must work to implement this kind of at least public alternatives to existing private offer, because as much regulation that you can put online, we think that there will never be sufficient if the power continues to stay on the side of big tech companies. Thank you very much for staying there, and if you have any questions, please feel free to do them.
Okay, thank you very much. We can have a couple of questions. So again, just feel free to just raise a hand and open your mic. No questions? So thinking? Okay, I see something in the chat. No, yes, one comment from Mariana, thank you. Okay. Okay, if there is no question, okay, there is one. So Samira, you want to just turn your camera and talk and your mic? Just put your question. No, I don't see. There are too many. Okay, so I read the question. Tiago, nice presentation. I am just wondering how can you distinguish agenda setting effects from normal effects?
Okay, thank you all for the appreciation, Mariana, Samira. First we have to define what are normal effects, right? I'm afraid I cannot infer what are normal effects. I understand more or less what you were saying, but first we had, in order to distinguish them, we had to define also what are normal effects. But according to agenda setting theory, is if you don't know directly your your political actors, and let's imply that if you are not related to some parties, to some party or directly involved in politics, what you know about politics is through the media. Therefore, everything that there is, or at least the great part of the debate which is generated on this, in this case on social media, it comes directly from the media. Therefore, this is I don't know if this satisfies your answer, but at least according to the theory, if you are seeing it somehow in the social media, is because the media somehow did their work in order for you to know their political agenda.
Okay, thank you. Other questions? No other questions? Thinking, still thinking? Okay, I just put one out of curiosity. You did not include any temporal dimension in the analysis, did you?
No. We didn't have the time to do. Yeah, that would be very interesting to do that and to see the evolution of the topics and see that evolution. But we didn't do that kind of experiments. But yeah, but it is a good idea.
Just to see whether, I mean, it's always interesting to see who leads who at some point, although difficult. Yeah. Okay.
Right, it will be difficult because we only have 4 days, and yeah, maybe things change in the last days, but yeah, nevertheless, it would be an interesting. It is an interesting question to pose. Yeah.
Okay, there is one comment from Mariana. People are skeptical about the possibility of digital social, the possibility of public digital social networks breaking the monopoly of large private platforms. What do you think about this possibility?
Well, okay, yeah, I am also with the fingers crossed, but we are seeing a political movement, as I said, in the United States, which would be more difficult to see this kind of political activity coming from, but also from with the European Union, with digital act services. So I think in people are more or less becoming more aware. People, when I say people, citizens, in the general terms, are becoming more aware, more or less aware to this kind of issues. So let us hope that they keep pressuring governments, but also governments are already doing something to break this dominance and. For the institutionalized actors and the traditional parties also, because it's not only the traditional media that are facing some challenges, but also traditional parties, as we saw in the terms of the Brexit and also right now in Brazil, new kinds of radical politics and right-wing politics are coming online, and some of them capturing the traditional parties, as happening in both countries. And if moderate parties and left-wing parties can do something about it, is through laws and having new kind of policies to break the dominance of big tech companies. And so let us hope that will happen somehow in the future.
Okay.
A question also, I don't know if I still have time.
There is, yes, there is one more. Could you explain again what the entropy is here? How did you get it from your data?
Okay. Yeah, thank you, Yiki, for your question. Here, entropy here, when we do topic modeling, we get a set. We use latent direct location. We get a set of vectors, and if you have a set of vectors, you can do all kinds of mathematical transformations upon them. We calculated the distance between them, and we got with Euclidean distance, and we got entropy by calculating the entropy of that set of vectors. This, from the theoretical view and from information theory view, this entropy regards the richness of the debate. If you have less entropy, we have a poorer debate and a poorer speech. If you have more entropy, then you have a more richer debate. This is how we define entropy here.
Okay, thank you very much. So now, as promised, we're gonna try to catch up where Ulrike end up, especially because I guess there are gonna be questions. I think there were some in the chat that I already missed.
Okay, can you take my presentation off? I'm not being able to do it, please.
But I don't see your presentation.
You don't see it? Okay.
Yeah, it's there. It's there.
Yeah, I'm on Linux, and somehow sometimes Zoom behaves a little oddly on Linux. If you can.
Oh, this is strange because I can't. Okay. Yeah, I see now. And how do I?
I will stop it, Laura.
Can you do that? Yes, please, because I don't know how to do it. Okay, thank you very much. Well, Ulrike, I tell you, we lost you in your last slide. Just if you want to put your co-workers, just not to let them like this, you can go. Otherwise, I give the word to people for questions. And I'm looking in the chat because I think there was already one, but it's so up. Okay, the question to Mariana, you answered her already on the chat, I guess. Right?
Yeah, and then there was a preceding one, but before that, I don't know if there was anything because you don't get to see with a chat when you
Yes, I know. You answer to Blas, I think. And I don't know if, okay, the best is that people just raise a hand and put the question so we don't lose time going up in the chat. And in the meantime, I'm gonna put one. At the beginning, in your very first model, when you were describing the different strategies that people have to evaluate the reliability of the sources, if I understand well, what people do, they evaluate the previous success of a people and some way of evaluating the truth, right? And there was an example in which you said that the earth is flat, and somebody who was at the moment you were trusting at some level tells you the earth is flat, and then you know that the earth doesn't look like flat. So if you understood well, you said I admit I go nearer believing the earth is flat, but I diminish the credibility of a person. And my question is how this catches up with the confirmation bias, because sometimes, I mean, people are take into account their own opinion about something much stronger than that. It's not just diminishing the credibility, but just even cutting links or things like that.
So yeah, thanks for that. So two observations. I think it's really important to distinguish, and I think this is one of the things I learned doing this work, between stuff where you can actually look at success with respect to past outcomes, right, which we call outcome-based updating, from this kind of expectation-based updating, because even in the flat Earth example, of course, I don't have certainty that the Earth is round or flat. I have a high degree of belief, but but it's still not fully resolved, right? I could still change my mind on that. And so the important thing about that strategy is that this is what people use when they don't know what the truth or falsity of the claim at issue is. They might think it's arbitrarily likely or unlikely, but they're still open to kind of change. And it's true, and you see that in the overconfidence data, and what I described as the ratchet is that strategy will look a lot like motivated reasoning or confirmation bias, in the sense that, of course, over time, the source that says something that's congruent with what I already believe will be perceived to be more reliable, and that sort of snowballs.
Okay.
But crucially, right, one of the things that's different from how people think about confirmation bias and motivated reasoning is that this agent is still only doing this over time. So it's using the present reliability to assimilate the evidence and then revising the beliefs, right? Which means that it's not strictly a confirmation bias, because if you imagine that you say a whole bunch of things that agree with me and I make you more and more reliable, and now you give me negative evidence, then I'm also going to go way further back, right? Because I'm going to use that degree of reliability that you'd got to. It's just that for the next trial, you'll be lower. And which is also why you see the overconfidence, particularly where the evidence is consistent, right? Because you're not getting something that forces you to. But so the really bad thing, I think, is that I think we all have the intuition. I've tried experimental paradigms to distinguish the two things, but it's hard. I think we all have the intuition that people already do that on the same trial. We do something even more extreme, right? Which is that we discount the evidence.
That was the sense of my question, yeah.
Yeah, exactly. And of course, that is just going to make things worse, right? That's going to make all of those effects that I showed you more extreme. It's going to give you more overconfidence, more polarization, more everything.
Okay, and the second question, when you were analyzing the influence of different networks, I noticed that you are using very, very small networks. And because of many other, opinion dynamics models and networks, we know that the size effects are crucial in the outcomes of the dynamics, and crucial, like really changing qualitatively by much large sizes. Is the reason why you use is there a reason why you choose or you need small networks, because of the experiments you may do in the lab or something else?
Yeah, so I agree. I agree that size matters there, and of course that was part of the thing of showing that these polarization effects are made worse by scaling the size of the network. They're small networks because it's actually the updating is it's quite computationally intensive. Right, because you're doing a kind of full Bayesian thing on it's not as easy as just propagating a bit of information at each.
Okay, it's a problem of computation. At some point I thought it could be related to experimental settings that you were trying to compare with, and in those cases
it is also that to the extent that I've run experiments that fit with this, those involve much smaller sizes. But yeah, even there, it's even in the experimental context, you bump into the computational issues, right? Like we were trying to run experiments with just kind of moderate size, for an experimental context, networks of 20 people, and the software that we were using for this just broke, right? Because so it is. Yeah, I would love to know what happens with these things when you make things kind of even bigger. I think you have two opposing forces, is my speculation, right? Is if I go back to the initial results on network structure and accuracy, I said that in that paper we examined the effects of topological characteristic standard networks of network topology on this, and path length is something that will make average path lengths is something that will make those effects better, and so there'll be some things that will be better in big networks, right? And then there will be some things like the polarization, I think that will get worse. And then it's just a kind of question of which of these forces outweighs, and presumably that will also be kind of highly kind of parameterization dependent. So I also suspect that there's not a single answer there anyway, right? Because the systems are just too complex.
Okay. There is a question of Maria Eunice. Do you want to put it the question by yourself, Maria Eunice? Just turn on your camera.
Yes, thank you, Ulrich. You suggested that we typically don't know the true reliability of our information source, and that at the individual and the collective level, agents' expectations might improve or provide amplified the intensity of for the weight of the evidence. So my question is that you say as it goes beyond our control, are you assuming that we have no autonomy, or the degree of autonomy in our opinions is very, very low?
Yeah, I think for me that's been the kind of the bottom line upshot of the work that I've done in the last 5 years, that I think we overestimate how much control we have over the accuracy of our beliefs. I think we like to think of ourselves as these very active epistemic agents who can do all kinds of things to sort of preserve the integrity of our beliefs. And I think that we overestimate that. I think we're really dependent, both if you think about what happens at the individual agent level and then what happens in a network context. I think both of those things conspire to make it the case that I think we're much more at the mercy of living in a benign information environment than we realize, and that we have historically realized. And I think that's one of the things that's going on at the moment in the world. I think it's also been interesting watching, I think on a kind of on a broader level, how the discourse about online social media has changed, right? When I started doing this work 5 or 6 years ago, everyone was still very much entrenched in this kind of, oh, these are just new technologies. It's just a platform. It's not changing anything substantively, right? And I think somewhere after the kind of US election in 2016, there's something there that flipped, where people moved to thinking, okay, I think there's something different going on here. We don't yet really understand what it is and why. Right, but I think we're only gradually waking up to the fact that changing the structure of our information environments, even on things that look at first instance unconnected to the accuracy of our beliefs, is going to have potentially really deep and consequential effects. I think that's something we're just also collectively have been learning over the last 5 and 6 years. I think that fits with what comes out of this. This kind of simulation work, because I think if you look even at these small simulations, even with small networks, right, the very fact that changing things gives rise to differences in accuracy. You look back with hindsight and think, like, how could we ever have thought that if we started to radically retool our information ecology, that wouldn't have effects on the accuracy of our beliefs, right? But of course, all of those are supra-individual effects. They're not, I'm just part of that network. There's nothing I can do, right?
Okay, well, thank you very much. I'm sorry we have to continue because we're already so late, and we could continue talking about that. Thank you very much for your great talk.
Thank you, and sorry again about the technical glitches.
So not a problem. Okay, so now I am gonna call Guillermo Romero Moreno.
Yes.
You're here. Okay, sorry for the delay, the technical problems that appeared. Okay, so the next talk is by Guillermo Romero Moreno, a joint work with Javier Padilla and Marcus Brede, and they are from the University of Southampton in United Kingdom and from the City University of New York. The talk is about the effects of party competition and consensus formation. Okay, 20 minutes.
Okay, thank you. Let's see, I hope that this works well, because also
It's perfect. I can see you.
Great, perfect, great. All right. So yes, hello everyone. Happy to be here. I'm going to talk about our work on the effects of party competition on consensus formation. Well, there are many works, studies that look at consensus formation and polarization in the opinion dynamics field. I'm sure you are very familiar with them. We are looking at these effects, this phenomena, but with the idea of including party competition in this process of consensus formation. So the questions would be like, what are the interference between the party competition in these processes? And here I highlighted two examples that, for instance, there is Brexit, in which the party competition was very strong and aggressive, and then there was this new issue that happened, it was the Brexit, and made the society polarized along this dimension, along this new issue. And it was very, very polarized in the sense that almost it was split like half-half, like half the population was on one side and everyone was on the other side, and they were very distinct. A similar example could be looked at in Catalonia, where there was also the issue of independence, that at some point in the recent years, there's been a stronger emphasis on this issue. And then also the political system was very strongly competing in this issue, and then the society was also split, and also very nearly like half of the population around. So there was a very clear polarization outcome. So we look at these questions of how this party competition affects polarization or consensus forming, and under which conditions this may happen. So we look at the bounded confidence model. I'm sure many of you are very familiar with it. It's a very classic model that has been studied for many years now. And it's an opinion dynamics model where the opinions are continuous in an interval, and then individuals interact. And then the interaction happens depending on whether the individuals interacting are close to each other in the opinion space. So if you have two individuals that are close to each other and they interact, they exchange information, and then their opinions get closer to each other as a result of this interaction. However, if you have individuals whose opinion is already too far away, so there's this bounded confidence threshold that sets these limits, then they don't interact. When they interact, they don't listen to each other, they ignore each other, or they don't listen to what they have to say, so nothing happens in their interaction. It's not a successful interaction in this regard. So there are many variants of this model. We are using this model, we are using it in 2 dimensions, and we are also including noise in the dynamic. So after every interaction, whether it's successful or not, we include a small random move, that is a Gaussian noise, to model things that are outside of the model, to include some noise. And then to this model of bounded confidence, we include the party competition. So party competition it's being studied a lot in political science. So we are joining this political science side to the opinion dynamics side. In political science, the spatial voting theory is very widely used, which says that people or citizens vote to parties depending on how close they are to the parties in the opinion space. So here you can see this individual here, and then depending on how close are to different parties, they would vote them with a probability related to this distance. So this is here, this is the probability of voting voter I at time t votes for party K. And this D would be the distance between the opinion of the voter and the position of the party. So then parties, they want to obtain as many votes as possible. So they would want to get the maximum expected vote share, the probabilities of all voters to vote for them. And then they will compete in the silencing domain. So we're assuming here that they have a fixed position, which is something that sometimes also regarded in the political science. They have a fixed position, but they compete not by changing their position, but they compete by campaigning. So by talking about one issue and then putting more emphasis on this issue. as Tiago has talked before, agenda setting could be, is the idea here. So parties, we assume that there are these different dimensions, and then parties, they can put weights on each dimension to affect how citizens perceive these dimensions. So they have these weights, they have to sum up to 1. And then the total saliency of how citizens perceive the dimension is going to be the average over the different preferred saliencies by each party. And then these saliencies, because they affect how users perceive dimensions, they affect how users perceive the distance. So the distance between them for the bounded confidence model, and also the distance to the parties for choosing who to vote. So there are these two effects by moving the saliency. And then we consider parties to be, with a simple algorithm, very myopic. So they will, every time step, they will change the saliency they are promoting, they should are promoting, by looking at the gradient of how to increase their vote share, and then making small steps in the direction, the saliency they promote in the direction that increases their vote share. So the models, simulations that we run are following the model that I have just explained. We are including 10 to the power 4, 10,000 agents. And then we started by sampling the initial conditions from our uniform random distribution. We include 3 parties and 2 dimensions. And then parties update the saliency, as I explained, every n divided by 2 time steps. And we run this until convergence. Once the simulation has converged, we look at the number of clusters that have been formed using the DigScan algorithm. And then we, instead of looking just at the number of clusters, because there may be some small clusters that form because of the noise or other aspects, we look at the effective number of clusters to have a cleaner measure of the system outcomes. So here I have an example, a sample simulation. So you can see here first on top, in the top left, this is the initial condition. And then at some point as the simulation evolves, here 2 clusters have formed, but there's a small path between them that eventually makes the 2 clusters to lead to a consensus. In the second row here, we have exactly the same simulation. We have the same random seed, so the initial conditions are the same, and then the different random parts of the simulation are identical, but we are including 3 parties here, and then with these different positions, and then we see that they are also affecting the saliency of the population, and then we see that instead of converging to a single cluster of consensus, we have 2 clusters that have been formed. So the population has arrived to a polarized state instead. Here in the bottom row, we have I'm showing some of the measures from the simulation. So you can see here the vote share on the left. This is the dispersion of opinions. And then here, these are the saliency that different parties are promoting. So in this case, the blue party is promoting dimension 1 with all the budget, because dimension 1 will give them more votes. And then the yellow and red party are promoting dimension 2. So because dimension 2 is being promoted by these 2 parties, more citizens are taking them into more consideration. This is the total, the aggregated saliency. So dimension 2 is perceived as double as important as dimension 1. And because of this reason, the polarization occurs along this dimension. People are taking this dimension more into account. And then the other one that could join some of the citizens is not taking them much into account, and then these 2 clusters emerge. So this is a sample simulation, but then we have run this across different randomsies and different simulations, realizations of the simulations, also with some other parameters. And then we see similar results. For instance, here, well, here you can see the results. Here in blue, this is the results with party competition. This is the effective number of clusters. And in pink, there's also no competition. So with party competition, you can see that most of the times there are 2 clusters emerging. This polarized state happens very consistently. However, with no competition, you can have either consensus, or at some point you get to a fragmented state with even 3 or 4 clusters. affecting number of clusters. So this could suggest that there is this polarizing effect. However, there is another case here where actually an opposite effect happen. So here, this is the particular competition, and in this case is converging to two clusters. And then when there is partial competition, in this case, consensus follows. So what is the difference here? Here parties are behaving a bit differently, in the sense that at the beginning, the red and blue party, they are promoting dimension 1. So actually 2 clusters would form along dimension 1. But then at some point, they rapidly shift their support to dimension 2. And then this makes the aggregate saliency to be shifted to the other dimension. So these 2 clusters that were very well aligned with dimension 1, suddenly they find themselves that dimension 2 is more important, and then that they are much more similar between themselves, so they unite. So in this case, there is a completely the opposite effect happening. And this also, it's consistent across different simulation runs and across different parameter settings. As you can see here in the blue, this is the outcome, the effective number of clusters on the party competition, and in pink when there's no party competition. So here the natural question that would arise is, what are the differences? Why in one case there is, or why sometimes there is this shift, or what would make this happen? So we are starting, but this is a work in progress. We're still working on this, but we are looking basically at this party configuration, party layout of the 3 parties. What are the features that may make them have one behavior or the other? So we have looked at 400 different random party layouts, and then looked at whether they led to one upon the other. 270 of them had some effects on the number of clusters that appear in the end. The rest, they didn't make any effect compared to no competition. And then from this, we've seen that the center of mass has been the main feature that stands out. So when the center of mass is in the center of the opinion space, this tends to lead more to consensus. There's this shifting mechanism happening more often. However, when it's a bit displaced, then you have more polarization. As you can see here, in this case, it was perfectly centered, the party layout, and here it was a bit displaced from the center. So in conclusion, we have seen here these 2 cases, and we are investigating a little more how party competition may affect consensus formation processes. We've seen that the main mechanism is that by putting more emphasis in one dimension and ignoring the others, citizens give more importance to this. They don't take other dimensions for getting consensus and speak to each other, so then more polarization happens. Although this effect may actually be reversed in some cases, where there is like rapid changes in the saliency that are promoted. So for instance, if you have some party system where different issues are being promoted very rapidly, like changing rapidly, this could have a different effect. And then we are still looking a bit further into this, is work in progress. So also any comments and suggestions on feedback about this would be greatly appreciated.
Okay, thank you very much. Is there any questions? Is there any question, singular? I don't see anything in the chat. Somebody raising hands? Okay, I have a couple of very quick ones. First one, which of the 2 models are you using here? Which are the results for the Fion or for Hexelman-Krause?
Yes, the Fion, yes.
The Fion, the equations you showed at the beginning was the Fion. Second question is, which is the, where are the agents? Is a full mixed population? Is a network? Is what?
No, it's a full
mixed population.
Yeah, full mix, yes, completely right.
And the third question that I saw at the last pictures that you put, I think that was the answer. How the critical threshold for consensus, when you have one, is modified with respect to the original model or without the interaction with the parties.
Sorry again, like the critical threshold for
you know that I'm talking about the bounded confidence interval.
Yes.
How is this modified when you get consensus? How is this modified with respect to the case when you don't have the interaction with the parties? I mean, do you bear agents that are more open-minded or less, or what?
Yes, for instance, you can see here in this graph here, this delta is the bounded confidence.
Okay, this is what I was not sure when I was looking at it. Okay.
Yeah, so you can see that in the case of consensus, yes, this is effectively displaced the critical bounded confidence threshold. So these effects are mainly or most notably seen around this phase transition from like the phase transition is shifted. So when you have this particular configuration, you will have in this case higher. Well, a lower bounded confidence.
They are both. I mean, you're on the two sides. That's why I was surprised of the value, which is a little bit smaller than 0.2. Yeah. Okay. Well, thank you very much. And now running, we go to the last presentation, and then it is me who has to share my screen and pass video. Okay, let me do that. Okay. So here I am. Tell me if you see the slides.
Yes.
Okay, right. Well, let's go, and then after the end, we get 5 minutes for questions. So let's wait.
We cannot listen.
There is no sound.
You have to share also the sound when you share your screen.
We cannot hear you. Laura, we cannot hear the what she's saying. There's no sound.
There is no sound in the video?
No, you needed to share the screen and the sound. So there is a configuration when you share your screen, probably. And then you need to click on shared sound as well.
If I knew where, I have to stop it. Okay, I'm gonna start again. Sorry, but it's not getting it. Okay, here I have, and you say that I have to, I should get something that allows me to, something which is advanced. Oh no. I was sharing a particular screen. I was not sharing my desktop, but I don't see anything that allows me to.
When you click on share screen and are selecting the window, then in the bottom left corner, there is a tick mark where you can tick.
Yes,
sound.
I can see that. Thank you very much, Henrik. What can I do without you? Okay, let's see if now it works. So let's go back.
Hi, good morning, good evening, good afternoon. First of all, I would like to thank Laura for the opportunity to share our work in this satellite. Thank you for the organization. and I'm Mariana, and together with my co-authors, Maria Eunice, Mariana Cláudia Brões, and José Arthur, I'm going to present the work entitled Big Data, Autonomous Actions, and the Dynamics of Opinion Formation. I would like to thank also the collaborators, and they are the members of the GAEC and CLE study groups, and also the funding agencies, FAPESC and CNPq, for supporting our project. The main objective of this work is to discuss the impacts of ICTs driven by big data on the dynamics of opinion formation. The central question that guides our work is, what are the possible implications of the extensive use of ICTs for the dynamics of opinion formation? Our working hypothesis is that ICTs driven by big data analytics might impact autonomous opinion formation by the growing process of mediating human daily activities through the automated generation, storage, and integration of personal data. As a methodology, we use literary studies together with a meta-analysis by analogical reasoning using particle swarm optimization algorithm in order to investigate the dynamics of opinion formation. I would like to invite you all to reflect with us around this theme, and let's start. Introduction. We introduce our work by remind of these famous dictums by McLuhan when he says the medium is the message. What does he mean? He says the medium is the message because it is the medium that shapes and controls the scale and form of human association and action. As an example, he brings the electrical light to represent the message, but not necessarily the content. The electrical light is a message because it does not convey a content, but it shapes our everyday lives. So when he says that the medium is the message, he understands that the message is not solely the content of a given medium, but also the structure of this medium. The message is that element that shapes, that changes the patterns, the structures of our practical activities in our daily lives. So McLuhan says that the content or uses of such media are as diverse as they are ineffectual in shaping the form of human association. What is important here to highlight is that the content of a medium has the potential to blind us to the very nature of the media, the structure of the media, that is itself a message. So in the era of big data, we can look at least to two different kinds of mediums. Here we are calling thin mediation and thick mediation. So when we're trying to communicate, you have this sort of thin mediation that can be exemplified by the telephone. What does it mean? It means that the aim of the telephone, for instance, is to convey a message from a source to a receiver, but not to retain the content of this message. So in a sense, the content of this message is ephemeral. It's not retained in some cloud or some databases. On the opposite side, we have a thick mediation, which aim is not simply to convey a given message, but also to retain this message, to retain not just the content of the message, but also the context of the message. For instance, not just to retain the text, but the way a given person writes on the keyboard or uses the mouse to convey this message. So what we are facing now is this possibility and this growing possibility to retain our personal data, to integrate the data in massive databases that can be powered by big data analytics. And in this context, the big data can integrate our data that with future repurposed, can be reused, can be recombined and reanalyzed. So our personal data is packed to travel. So we can travel and we don't know what could be done. So when we say that the mediation is thick, although its content is visible and diverse, its nature is invisible and ubiquitous. So the very structure of the media powered by big data analytics, this what we are calling here thick mediation, is invisible to many users. And this invisibility can affect individual and collective process of autonomous opinion formation. And here we understand that this process of autonomous opinion formation, when the establishment of a given opinion network occurs in a self-organized manner. So what will be autonomy here? We characterize a person that has degrees of autonomy if the person P possesses a reliable anticipatory information of choice opportunities for actions. And also if the person P has the capacity to choose regardless coercive external pressure. In the context of thick mediation, we could think that the person P possesses reliable anticipatory information of the content and the nature of the media, which allows choice opportunities for actions, and also will have autonomy if it has the capacity to choose regardless of coercive external pressure. So what could we think or reflect about these dynamics of autonomous opinion formation in the era of big data? Remember that with the advance of ICTs, or information and communication technology, agents that were once separated physically and geographically distant, they can have now the opportunity to come together, mediated by this thick mediation, and they can form groups with different opinions. So we are asking here, what will be these possible consequences, the positive and negative consequences of these new possibilities of shared opinion formations? To help us think about these possibilities, we bring Garfinkel's hypothesis, according to which the constructions of the social world through practical knowledge enables the common citizen to act with reflexive ability to interpret and even resist certain social norms. This reflexive ability is precisely the ability to not just see the content of the message, but its very nature, how the message is conveyed, what's the structure behind the message. Assuming that the medium is the message, is it possible to model Garfinkel's hypothesis? And here we use particle swarm optimization to try to understand these self-organizing processes of autonomous opinion formation. Here, the dynamics of opinion formation is represented by an evolutionary network incremented with particle swarm optimization algorithm, where nodes represent the agent's opinion and edges indicates types of self-organized relationships. By using this PSO algorithm, we came with at least 4 possible outcomes. First of all, it will be a consensus when groups of people interact and they take into account the local and the global opinions or possible opinions to form a set of opinions in a self-organized way. That will be ideally what could happen in a society. But we also have polarization when we have 2 different opinions that oppose each other. We have fragmentation when many opinions and different opinions are scattered through this landscape, that is the context. And finally, we have the possibility for inertia or indifference when the status quo remains as is. So as an example, we can think about this retweet network built up by Alfano et al. Their aim was to use emoji and hashtag use to see if they could identify different groups that share different opinions. And the result is very interesting because they identified 4 groups, among which 3 shared a common opinion that is in favor of the Black Lives Matter protesters, and the other group that's in red, it's not in favor. So we have a sort of partial consensus among 3 different groups, but also a general global polarization with 2 different groups. So on final remarks, we reflect upon the positive and negative ethical implications. So on the one hand, big data processes might allow autonomous opinion formation by exposing the content and nature of shared messages through thick mediation, empowering collective practices, helping to strengthen the voices of minorities. However, as in the negative side, the use of big data analytics can also threaten people's privacy and autonomy, even when people are aware of its content and nature. By identifying the political, emotional, and ideological features of people, big data strategies could be used for surveillance, negatively affecting the dynamics of individual and collective autonomy, and consequently, the possibility of autonomous opinion formation. So the medium as the main message. In the context of social media, the medium is often the main message. With the growing process of mediating human daily activities through the automated generation, storage, and integration of personal data, we have to challenge the impact that thick mediation has in the dynamic process of autonomous opinion formation by exposing not only the content of the medium, but its very nature. Here's the references. And thank you so much. I'm looking forward for the questions.
Okay, thank you very much, Mariana. I have to start by a very deep apology because with all this technical thing, I forgot to introduce the author. So let's just catch up with that. So the speaker is Mariana Viti Rodriguez, and it was a joint work with Maria Eunice González, Maria Claudia Broens, and Jose Artur Quilich González. All of them from the Faculty of Philosophy and Science from UNESCO, Brazil. So sorry really for that. I was so worried about dealing with the video that I forgot that. Okay, so let's take 5 minutes for questions because in fact you ended up a little bit earlier. Is there any questions about that? I don't see, let me see chat up. Okay. I don't see. Okay, congratulations from Maria. Okay, if there is no questions, I have one. Can you please detail a little bit more the model with the swarm optimization algorithm? So what are the elements of a node? What are the nodes? What do the links mean? I really got lost. That was too quick for me.
Yes, okay. We were thinking about this model as a way of better understand, and even if as a way of an heuristic to see what would be the possible outcomes. And what we like about this model is that we have particles, and these particles means the agents and with its current opinion, and then you set up the model when the model starts. the agents not only considers their opinions from past experience, but they also considers the global opinion. So if you change the model and you change the landscape, also the landscape of the model is full of hills and valleys, and these hills and valleys, they represent the possible, well, in physics we will say the minimal energy. So the minimal energy will be the best opinion. And so when you set that landscape that can be smooth or not, you will have the best opinion formation that will form a consensus that ideally will be the best for society. But then, and then what we like about that is that we can model the self-organized matter, how opinions change, because the particles can, depending on how you set up also the parameters, we have basically two parameters. We have the velocity and the position of the particles, and they will be randomly assigned for start the model. But then what happened is that they will consider not just their own past experience, so the P best, that will be the best opinion for this particle, but also the global best, that will be the best opinion for all, or I mean, the global, that will be for the best opinion that the particle has found according to the true best, that will be the minimal point of energy in the landscape. Is that clear?
More or less, I try. So you have an idea of cost function of or energy or something like that, and which are how do you set up the interactions between the different agents? Where they are in a network, there are in continuous space. It's like a big shakes model of flocking. How does it go? How the agents interact? I did not understand that.
Yes. Yes, I don't really understand the technical details, but I know it is inspired by like the swarm or flock of the birds, but they are not interacting with the distance, because then you have a conflict, right? They are understanding, they are interacting with the distance with the best opinion. So they will be, is that close to the true best point of minimal energy? So this is, they are interacting like that, as far as understood. I don't know if Nisi would like to add something on it.
Okay.
Yeah.
Okay. Okay. Thank you very much. Any other question? Okay. Well, let me see the chat. I don't want to close out anybody. Okay. Okay. Well, if there are not more questions, we thank you very much again for your presentation. And well, this is a moment to wrap up. It's very late, so I'm very thankful for all those that are still here. I'm very thankful for this very interesting satellite. I think it was very it's variety of approaches to the problem. I'm very happy about that. A little bit pessimistic from informational point of view. If we take out the message from Filippo that tells us that we are very easy to manipulate, the message from Ulrike that tells us that we cannot trust our own judgment, and now Mariana telling us that even the structure of the channels of communications are a problem. Well, we are in difficulty, but there is at least there is a lot of work. Well, thank you very much for your participation, and well, let's enjoy the rest of the conference for the other days. Okay, so bye bye. Bye to all. Bye bye.